right, for this first one, as we can see, we have that the annual, the mean annual temperature for Earth recorded at 50-year intervals are shown in the table. So these temperatures are all mean annual temperatures, and as we can see the 50-year interval, here you have plus 50, here you have plus 50, etc. Okay? How do you read this? Well, I don't know. In 1908, the mean annual temperature was 9.13 Celsius. All right, so that is like the context. And then our good old friend Tami creates a linear model for this data by finding the equation of the straight line passing through the points with coordinates blah and blah. Okay, so they are using this point and this point. We need to calculate the gradient of the straight line that passes through these 2 points. Now, first things first, a little bit of context. So notice that they find the equation of the straight line passing through those 2 points. See? And notice how the temperature goes changing. For example, from here to here, it went down. It went down just around 0.12. Then it went up plus 0.02. Here it went up plus 0.01. If it was a straight line, all of these numbers would be the same, but they're not. And so let's really understand what Tami is doing. Technically, if you take, like, I don't know, if you draw the graph, right? And here you have, actually, yeah, let's make it like this. So let's say that here you have temperature, and here you have time. There's a bunch of dots in between, right? And technically there's a curve going along it, see? And so what Tami is doing by taking a straight line of 2 points is that we are calculating this straight line, okay? We're calculating that straight line. We're ignoring the parts with a curve. We're actually not making a curve. We're making a straight line. So just so that we understand a little bit the context and what's going on, okay? All right, enough blah blah. For part A, they ask us to calculate the gradient, what the fuck is that, of the straight line that passes through these 2 points. And so gradient, and actually let me pull something up over here. So for gradient, we have the famous formula booklet. A good thing to have in mind, you guys, is that the day of the test, you're walking in with just a couple things. You're walking in with a pen and pencil. You're walking in with all the motivation in your brain. You're walking in with 2 years of studying the IB, and you're also walking in with 2 hours of sleep. You're walking in with your graphing calculator and the formula booklet. Guys, these last two, the formula booklet and the graphing calculator, are tools. Okay, they are tools that will be available the day of the test. So it's important to get familiar with your tools so that the day of the test you can use them. Okay, and so why do I say this? Because you might be reading this, you read the word gradient, and you're like, fuck, I don't remember exactly what it is, but I know it's in the formula booklet. So you open up your formula booklet, you go to wherever it says gradient, there it is. And this helps you refresh your memory a little bit. So what the heck is gradient? Well, this is in the context, or it's in the same block, right? It's in the same block as equations of a straight line. Ah, okay, so this m is also this m, and also this m. Okay, and now it makes a little bit more sense. Okay, so here up top we have technically how y changes, and on the bottom we have technically how x changes. Ah, okay, so this is slope. This is slope. And as some of you might have heard, well, how does y change? How does it rise? How does x change? The horizontal one, how does it run? Some people have heard of rise over run. Some people just hear of slope. Some people hear about change of y and change in x, rate of change. There's a lot of different ways to say this. What am I trying to express? Gradient is the same as slope. Okay, so it's how your line changes. See, for example, a line that looks like this, let's say this has a slope of 1. Well, something that goes like that will have a slope of -1. See? And something that it grows faster will have a greater slope. right? So like m equals, I don't know, 10. And something that grows like slower, but in the negative side, would be a slope of, I don't know, negative 20. Okay? So that is slope, that is straight lines. Let's get to it. See, so the gradient formula, as we can see here, is y2 minus y1 divided by x2 minus x1. So m equals this. Okay, so what the heck is y2? What is y1? What is x2? What is x1? I got you. Relax. So x2 and x1 and all this shit is just expressing a point. Okay? Chill out. For example, point 1 or whatever. Point is x1 goes with y1. x2 goes with y2. Okay, this is just expressing a point on your graph. Okay, for example, you might pick, honestly, you might pick that this is your x1, y1. So x would be here. I mean, x1 would be here, y1 would be here. See? Or you might pick for this guy to be y2 and x2. So this point here would be x2, y2. Okay, it's literally just points on your line. See? And so here I have 2 points. See? And you might be thinking, damn, which is the first one? Which is the second one? Dude, as long as you're consistent, it's going to work. See? So let's do it the most intuitive way possible. The first one that shows up is going to be x1, y1. The second one that shows up is going to be x2, y2. And so I go ahead and plug in. So y2 is 9.45 minus y1, which is 8.73. All of this divided by x2, which is 1958, minus 1708, x1. So trust the process. Here's the formula, no worries. I plug that into my calculator. There's an easy way to plug it into my calculator, okay? Because I have a fraction, you can press alpha and then y equals. Alpha y equals, you hit that F1 button, brings up this menu. There's a lot of stuff on it, but it's just fractions. The first one is a fraction. So here you can put 9.45 minus 8.73, 1958. This is just a calculator trick to get it faster, okay? That's all. You end up with 0.00288. What might have happened to you is that you got the answer in a fraction, okay? You might have gotten it in the answer of 9 divided by 325. See? You might have gotten it like this, and you're like, damn, why don't I have the decimal? Well, if you don't have the decimal, you can find it like this. And so in one hand, you have it expressed as a fraction. In the other hand, you have it expressed as a decimal. It's the same number, okay? Actually, you can leave your answer as a fraction. Let me just show you the answer key real quick. You can leave it in either of the two ways. See? I'm just saying, like, if your calculator is giving it to you in fraction and you're freaking out, just don't freak out. It's all right. It's normal. And if you want it in decimal, well, just write it again, but with a division symbol. See? All right, whatever. Part A, M for part A is going to be, as we said, 0.00288. So let me just go like this, leave it nice and pretty, and check. For part B, part I, we need to interpret the meaning of the gradient in the context of the question. All right, so technically, the gradient, as we said, is a little bit like rate of change. See, here I mentioned the rate of change. And so, this slope is how x relates to y. See, it's a way to interpret how x relates to y, and in the context of the question, I have year on x, year on my x, and temperature for y. And so a slope of 0.00288 means that as the years go by, temperature increases. And that's it. Okay, so technically the gradient would be the yearly change in temperature. And notice, you're always going to be expressing like whatever x is. So technically, like the original definition, I should have started here. The original definition is kind of like um, the change in x causing a change in y. And so what is x in this context? It is time, it is years. See? And so the change in x causing a change in y, the, the change in years causing a change in temperature. All right, this is like the very intuitive way to put it. And let's recall that here they talk about the mean annual temperature. And so, oh, and also we talk about mean annual temperature. And so technically, if you want to get a little bit fancier with this, you can say the yearly change, right? The mean yearly change in mean annual temperature. Why annual? Because we have annual temperatures up there. See? All right, so I just want to show a little bit more intuitively. You're always going to be expressing x and then y. X was years, y was temperature, right? X is years, y was temperature. And then we plug in the buzzwords that they said, mean yearly, right? Mean annual. So that is just a very more thorough way to put it. All right, whatever. That is for part I. For part double I, we need to state appropriate units for the gradient. All right, so again, part B is like a full-on context question. See? And so what units am I working with? Well, we already noticed earlier that we have mean annual temperatures. But in what? In Fahrenheit? In Celsius. Okay, so we're going to be talking about Celsius. Every how much time? Ah, every year. All right, let's boil this down a little bit. See, so from top to bottom, what do we start off with? We start off with, we are talking about temperature per time. Temperature per time. And which temperature are we talking about? We're talking about Celsius. So Celsius, I don't think I'm writing that correctly, but I don't care. Celsius, and how much time? Year. And so this allows you, and this is the answer key actually, you can talk about Celsius per year. Another way you can express it, in case it makes you feel a little bit more comfortable, you can talk about degrees Celsius per year. Okay? Both of these last two are in the answer key, trust me. Find your way to express it. Okay? Whatever floats your boat. But start from the tuition. In general, we're talking about temperature and time. Which temperature? Celsius. Which time? Per year. Appropriate units for the gradient? Celsius per year. That is for part B. A small comment I would like to make. See? Part B, usually, and in some of my videos I talk about this a lot, what you need in part B is something you needed in part A, right? But this is an excellent example of that not being the case. And you might be telling me, well, why does that help me? It helps you because the day of tomorrow, you might be mega stuck on part A, but you realize, yo, part B doesn't need anything from part A. Actually, part B is a context question. So what does that mean? Maybe you're running low on time. Maybe it's near the end of the time of your test and like whatever, you're like freaking out or whatever, like, oh, where can I get points? Part B is a context question. It doesn't need anything from any of the other parts. Interpret the meaning of the gradient. It's not telling you to get the gradient. It's telling you to interpret the meaning of the gradient. So I'm just pointing that out, that part B, you can do it without part A. It's good to notice when it's the case to earn some free points if you're running low on time and stuff like that. That's the only reason I'm pointing it out. Now, The IB being the IB, for part C, we need to find the equation of the line giving your answer in the form y equals mx plus c. Notice how we need m. And what is m? M is gradient. So in this case, part C needs something from part A. Interesting. Why is this worth knowing? Because it's a hint of what you might need to do or the path you need to take if you realize that if you realize that part C needs something from part A. Usually it's that part C needs something from part B, but part B is a context question. I mean, guys, this could have been like the last one. You know, it could have been like H or whatever. And that wouldn't change anything in your process. It doesn't change your process. It helps you understand better, yes, but it doesn't change your process. So it's good to notice which parts need each other, which parts don't need each other, and use that itself as a hint. So I just added a tool to your toolbox. I hope it helps. Whatever, part C, find the equation. So it is asking us to give it in the form y equals mx plus c. And yes, it's true, you can get there like pretty quickly just by plugging in. But let me give you the more conservative approach. So when we look at the equation of a straight line, y equals mx plus c is right here. Okay? Now there are two other ways to express the same thing. You have this one in green. Well, let's put them all in green. So you have that one in green, this other one in green, and this last one in green. Guys, you really need to understand the following. These three equations are the same thing. They're the same thing, just like moved around a little bit. Okay? And so you can start in any of these and reach any of the other forms. Now, what usually happens? What usually happens is that the one in the middle, no one cares about unless they ask you to answer in that form. Honestly, no one cares about this one unless they ask you to answer in this form. What usually happens is that you go from this one over to that one, or from this one over to they ask you to answer in this form. Okay? Why do I urge you to start from this one? Because this one is usually all you need in order to create the equation of a line. Why? Because this one on the right side, well, what does it ask for? It asks for m, so you need m, and it asks for x1, y1, which is a set of points. Usually, you guys, finding a set of points and finding m is not that hard. Okay, it's super doable. You can do it. See? On the other hand, this one on the left side, what does it ask for? It also asks for m, so that's something that they have in common, and it asks for c. Now, c is the y-intercept. And so, do I have the y-intercept of my equation up here? No. Is there a way I can get it using the equation on the left? Yes. Is it intuitive? No. Which is the most intuitive option? The one on the right side. So fuck you, we're using the one on the right. So the one on the right, we're gonna get to this form eventually. Okay, so trust the process. Just get used to using the one on the right because it's the most friendly option. Okay, so let me make some space down here. Da, 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 da. As I said, my equation is from the formula booklet y minus y1 equals m parentheses x minus x1. Okay, so which point am I going to use? Doesn't matter. You pick. I'm going to use this one. You can use the other one. I don't care. So we know that m is. Actually, let's go piece by piece. So y1, we're saying is 8.73. Cool. 8.73. M is 0.00288. 0.00288. Parentheses x minus x1. 1708. Cool. Notice how I didn't plug anything in for x and y. See? That's fine. Relax. Don't worry. If you notice this form over here, y and x is also going to remain unchanged, but you will plug in for m and you will plug in for c. How do you get c from here? Just trust the process. Okay, trust the process. Get this line. Find your way to reach y equals mx plus c. Okay? Go from this to that. go from this to that. That is our goal. Trust the process. If you learn all these different processes, you're for sure going to get a 4 and probably a 5. Okay, learn the intuition of the problems, learn the procedure, learn the method. That is the most important part. Learn the method. So you make it an equation of a straight line. Start with this guy. It's the most friendly one. And then reach everything else. See? All right, what do I do from here? What I suggest is first deal with this parentheses. So multiply here, multiply here. So y minus 8.73 equals 0.00288x minus whatever that number is we're about to find out. So 0.00288 times negative 1708. There it is, minus 4.91904. Okay, so get y alone. See? Get y alone. Y is not alone. It is being affected by minus 8.73. So we're going to add. We're going to add 8.73. This goes away with this. Plus 8.73 on this side. So I end up with y equals 0.00288x plus something. So this plus this. Lo and behold, plus 3.81096. Does this look familiar, you guys? It damn better look familiar because this is just the same as y equals mx plus c. Ah, okay. So what's my y-intercept? My y-intercept is 3.81096. And my slope, well, my slope is right here. My slope, 0.00288 is my m, which is what I got over here. Wow, this is magical. No, it's not magical. It's called knowing the procedure and always starting from this one. See? Technically, if any of you noticed, I'm just going to show it quickly. You can use the one on the left. I'm not going to do the whole process, but you can figure it out yourself. So the one on the left is y equals mx plus c. And technically, because you already know m, you can plug in m. So it's 0.00288 x plus c. And here you can also plug in a set of points. You can plug in x, you can plug in y. And so same thing, you can plug in y, so 8.73 equals 0.00288 times x, which is 1708, plus c. And so this can give you c. And now that I'm doing it, fuck it, I'm just going to show you. So 0.00288 times 1708. Yeah, that gives you that number. So 8.73 equals 4.91904 plus c. So c has to be 8.73 minus this other guy. So c has to be 3.81096, which is the same c that I got over there. And so then you can plug this back in over there, and you end up with y equals 0.00288 x plus 3.81096. I know some of you might be thinking, okay, you just showed me two ways, and it was way faster than one on the left. And I'm like, yes, it's true, but I think way more intuitively is this guy. Okay, I think it's more intuitive. Getting the y-intercept can be a little bit weird to plug in x and y. I know for some people they're like, huh? Because it is weird. This is the weird but fast way. This is the conservative, a little bit longer, but reliable way. All right, find what works for you. I'm just showing you the tools. I suggest the old reliable. See? To each their own, whatever. So for part C, well, we did it. See? So for part C, the equation is, just to write it down, y equals 0.00288x plus 3.81096. Yeah, then for part D, we need to use Tami's model to estimate the mean annual temperature in the year 2000. All right, so the main idea we have to capitalize on is we are estimating what thing? We estimate the mean annual temperature. Okay, what is mean annual temperature? Mean annual temperature is, it's my y. So we're estimating a y in the year 2000? The year 2000, what is it? It's x. Okay, so if they tell me year 2000, that means x equals 2000. And so we're going to plug in x and figure out my y. Pretty simple, right? So I plug in 2000 for my x and figure out my y. 96. Just so that we're all on the same page here, technically what I'm doing when I plug in 2000 here is what is y when x is 2000? Okay, that is all I'm doing. What is y when x is 2000? Which in the context of the problem is what is the temperature when the year is 2000? Now, of course, this is an estimate because Tami's model is trying to estimate, right? But this is the context, see? You ask the function, what is y when x is 2000? That is all you're doing. So plug into your calculator. Let's see what happens. 0.00288 times 2000 plus 3.81096. Correcto. There it is. And so technically you can write that the answer is 9.57096. Put the units Celsius. If you want to do it to three significant figures, you can count 1, 2, 3. Do you round this one up or down? You keep it the same, so it stays as 9.57 Celsius. That is for part D. Again, not that hard, but really understand the context of what you're doing. You're asking the function, what is y when x is 2000? Y is temperature, x is year 2000. Then we have our buddy Thandizo use a linear regression to obtain a model for the data. And so for part I, we need to find the equation of the regression line y on x. So remember how I said earlier that technically this graph, I don't know, looks probably something like this, right? And you have like a curve, right? So here's the thing. What Tami did, all right, from parts A to D, what Tami did was find the equation, I don't know, like from here to here. See, the straight line from there to there. Okay? And what Thandizo is going to try to do is that he's going to take all these different points, everything in between. He's going to take all these different points and find what we call the regression line. Okay? And just very, very intuitively, the regression line is just sort of like the average of all these points. See? So the average of all these points, if you draw a line, would probably be something that cuts like that. Okay, so it's a little bit different than Tami's line, but that's the main idea. See? For example, if you have, I don't know, like a scatter plot that looks something like this, and it's sort of aiming upwards, the regression line would probably look something like that. See? If you have a scatter plot with a bunch of stuff sort of like aiming down, then yeah, I mean, your regression line might be a little bit off, but it's going to be like aiming down a little bit. See? So that is what the regression line does. That's why it's useful. It can help you estimate, which we actually do later. But we will see that in a second. See? So the equation of the regression line, y on x. We understand what they're asking for, but maybe we don't know how to do it yet. See? And here is where, remember how I mentioned in part A, that you gotta get used to or get familiar with the formula booklet because it's one of the tools you're gonna be using. Well, there are two main things you gotta get used to. No sleep. The formula booklet, it's actually three things. And the graphing calculator. See, get familiar with it. There's a lot of tools in there. See, and so the idea is that the moment you read the word regression, you immediately think that is in my calculator. Maybe you're not sure where, maybe you don't recall exactly its location, but you know it's in there. You know that shit is in there. So you pull out your calculator and you're like, damn, this guy on YouTube said it's in here. I know it's in here. I've used it before. where the hell is it? And you're gonna start, you're gonna start looking everywhere, like here, there, blah, blah, blah. Like, okay, go piece by piece. This is a regression line. You're trying to estimate something. You have a linear model. So, you're estimating stuff. Okay, you are in the world of statistics. So, kapow, you press the stat button. Okay, so I can edit, I can calculate. There are tests. Eventually, you're going to find that in the calculate tab, down here you have line reg. Notice how it says line reg ax plus b. So it's literally a linear regression of a straight line. Ax plus b makes reference to the famous y equals mx plus c. Okay? So, you press linear reg, see what it asks for. What does it ask for? It asks for an x list, it asks for a y list, the frequency list only if it's necessary, and you can store your regression equation in one of your y equals. Oops, that was not what I meant to do. Although that looks really cool. Damn. And you can store your reg EQ if you want to. See? In one of your y equals. For example, you want to store it in, I don't know, y2. It's going to show up in your y equals on y2. See? How did I just do that? I pressed alpha, trace, and hit F4. See? I don't think you're ever going to really want to do this, but you can. That's all I'm saying. See? All right. Whatever. So, we find line reg. We see what it asks for. We need the lists. See? Where did I change the lists? I forgot. Go to stat, edit. You want to edit your lists. Go stat, go edit. Boom, there it is. See? You probably have a bunch of stuff from another exercise. That's cool. Go ahead and clear those lists. See? A quick way to do it is go up top on the title L1, clear, enter. Clear, enter. Cleans it up right away. Nice and easy. So, as we said or noticed in line reg, L1 is X. L1 is X and Y is L2. Okay, so which one is X in this context? X is literally year. See? So we're going to put all my years on my L1. 1708, 1758, 1808, 1858, 1908, 1958, and 2008. Take a second, check your work. It's always worth it. So this is fine, 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 fine and dandy. All this beautiful in the world. Cool. So that is X. Now we put in my Y values, which is temperature, my Y, my X, my L2. So 8.73, 9.22. Oh, small mistake. Happens to anyone. Beautiful. 8.73, 9.22, 9.10, 9.12, 9.13, blah, 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 blah. All right, cool. So now that we plugged everything in and we double checked and everything is nice and dandy, we can go back to the line reg thing. See, so if I go to line reg, well, I have my X list, I have my Y list, and I'm going to store my equation just because I want to. See, whatever. I'm going to put it in Y1. This is unnecessary, but it's cool to do it. See, there is no frequency list. If you had a frequency list, you would put something here, but I don't. So unless they give you a frequency list, you should just never worry about this, okay? Go ahead and press calculate. Boom, there it is. See? So it's telling you that for the equation of y equals ax plus b, which is the same as y equals mx plus c, ¿vale? Your a, which is your slope, is going to be 0.0025, and your y-intercept is going to be around 4.4. Okay, cool. So for my answer, I can write y equals 0.00256. Yeah, let's leave it at 256. Three significant figures. You count 1, 2, 3. This fifth one to the right. Round it up. Blah, blah, blah. X plus the y-intercept, which is count 1, 2, 3. This 6. Do you round it up or down? You leave it at 6. Okay. 4.46. So here is part E, part I. See? Cool. Then they tell you to find the value of R, the Pearson's product moment correlation coefficient. What the fuck did I just read? You need to find R. Let me just erase this for a sec. You need to find R, the Pearson's product moment correlation coefficient. Okay, this is probably the biggest buzzword that you're gonna have to learn. Okay, the biggest vocab word that should jump out to you and be like, whoa, if I see this, that means I need to do that. See? So the value of R helps you understand a little bit how your how your linear regression relates to your data. For example, this line in orange, okay, probably has an R like near 1. See? It's very aligned with my data, and an R value of 1 means that it's like it cuts through your data very closely. It's a good estimator, like it correlates well. See, there's a correlation. What is correlation? Well, as x increases, so does y. See? And so something that can be correlated is like, dude, I don't know. Amount of sunlight the plant has and its height. And so the more sunlight it has, the higher it gets. It kind of makes sense, right? Or I don't know, like just whatever. See? Correlation, there's a lot of examples, I'm sure you can find them. R helps you identify how strong that correlation is. And so a correlation of, I don't know, maybe like near 0, so near 0 would be like a line that's something like this. Maybe your data is all over the place, right? It's all over the place. It wasn't able to do a good correlation. An R near 0 would look like that. See? There is no correlation between your data. Everything's just kind of random. See? Yeah. Whatever. So that's the idea of R. Pearson's product moment correlation coefficient. Yeah. Sounds fancy as fuck, but it's just correlation. So you stick to that. It's just correlation. And so your calculator should be giving you the R value when you do line reg. Okay? In fact, some of you probably already have it, and they're like, why does yours not show up, dude? You're like a fucking loser. Why doesn't it show up? Well, it's not that you're a loser, it's that your calculator does what it asks, does what it is asked to do perfectly. Sometimes too perfectly. See? If you don't put in that extra parentheses, or you don't ask for it to give you R, it's not going to give you R. It just doesn't care. For some of you, it shows up because you already put the setting beforehand, but for those of you that it doesn't, you have to go to mode. Okay, this button next to the blue one, mode. And here there's a bunch of stuff that you should always keep the same. And one of them down here is stat diagnostics. Don't keep it off, keep it on. Why? Because now the next time you do line reg, keeping everything the same, kapow! You get extra information and there is your R value. Your R value is going to be 8, sorry, it's going to be 0.861 significant figures. See? There's your R value. See? And so notice how part E really, you just needed to be good with the calculator. It wasn't being like savvy at math and good at this or that and knowing all these math tricks. Nah, dude. It was just knowing what your calculator has, knowing its capabilities, and knowing where to find it. That's it. I insist, you guys. A big part of this course, in my opinion, is just managing the graphing calculator. Straight up. For almost all of these statistics parts, it's just knowing the tools that you have and knowing what they do. So get used to it, practice it, get familiar with the formula booklet as well. See? The day of the test, no sleep, formula booklet, graphing calculator, and a couple other things. See? But the main things are these. These are the main tools you're going to use and have, so practice with these. Do your homework with these. Love them, because they're going to save your ass the day of the test. All right, that is part E. See? Part F, we have that we need to use Thandizo's model to estimate the mean annual temperature in the year 2000. So notice how this is pretty much the same as part D, just that now we're using Thandizo's model. So, again, same thing. X equals 2000 because we're talking about the year 2000. And we need to estimate the mean annual temperature. What was temperature? Temperature was Y. So we need to find the Y when X is 2000. This is literally the same as part D, just that with the new equation. What is the equation that we're using now? It is right there. So we're going to be putting 2000 into that. See? This will look better. So we have 0.00256 times the famous 2000 plus 4.46. There it is, you guys. There it is. For part F, we have that the mean temperature for the year 2000, according to Thandizo's model, is 9.58 Celsius. All right, so Tami's model and Thandizo's model were incredibly close. I mean, Tami's is 9.57, Thandizo's is 9.58. I don't know which one is better. It's not part of the question, but it's cool to think about, right? Which one ended up being more accurate? I don't know. Anyways, then they tell us that Thandizo uses his regression line to predict the year when the mean annual temperature will first exceed 15 Celsius. So we need to state two reasons why Thandizo's prediction may not be valid. Alright, and this part is a little more theoretical, it's a little bit more intuitive actually, and we need to talk about a regression line why a regression line might suck at predicting. Why would a regression line suck at predicting? On the one hand, you have this thing that they call, and this should come to mind immediately, at least in the future, this thing called extrapolation. And so extrapolation is a little bit like the, let me explain it another way. See, so extrapolation is a little bit like, let me make some space for my homies. Yeah. Extrapolation is a little bit like you have your graph over here. See? And let's say, oh, here's a good one. So here you have test score, and here you have time studying. And so according to this, the graph would probably look something like, it's probably gonna grow like really fast, right? It's probably gonna be something like that. Like the more you study, the better it's gonna go for you. See, so probably something like this. See? Yeah. If you use extrapolation here, you would conclude like, oh, eventually, I'm gonna score 1,000%. Guys, does it make sense to score 1,000%? Nah, dude. Your maximum is 100%. And so extrapolation, what it kind of does, that sometimes it's right, sometimes it's wrong, is that it takes a picture here and it says, okay, how would the picture look if it was bigger? See? And sometimes it doesn't make much sense to reach 1,000%. See? And much like over here, you see how the temperatures are slowly growing. Well, when you extrapolate, you're assuming they're going to keep growing like this always, right? But how much will it get to grow, right? How much, what is the limit? We don't know. Now, I don't want to get like all, like polemic or whatever. Like, we're talking about global warming basically. But stat- from the angle of statistics, in just this exercise, okay, this is not like mega professional or anything, but in just this exercise, it's hard to extrapolate so far out. Okay, that's the whole point. These temperatures are around 8 or 9. And you're trying to extrapolate, like all these years, around 8 or 9 or 10. See? It doesn't even reach 10, but it's close to 10. See, it's around 8 or 9 or 10, and you're trying to extrapolate all the way to 15. Okay, that is way out. It is way different than the data you have at hand. And so, one argument for why the regression line might suck at predicting or not be valid, one of them is extrapolation. You literally just put the word extrapolation, and they're going to get it. In fact, in your answer key, it says just extrapolation. You put the word extrapolation, boom, you get a point. Easy as that. See? So, on the one hand, you have extrapolation, which for a regression line, it's just, it can make it not valid. See? It might be, it might not be, it can make it not valid. It is a reason. All right, on the one hand, we have that. See? The other reason is a little harder. See? Let me tell you why. Notice for part F, when we used Thandizo's model to estimate the mean annual temperature in the year 2000, we were plugging in an x. We were plugging in an x in order to get a y. In part D, we were again plugging in an x in order to get a y. And over here in part G, technically they're asking us to plug in a y and get an x. And regression lines, this is just like a mathy thing, but regression lines are good at doing it the other way around. They're good at finding y through an x. They're not as good as finding x through a y. It's not that they can't, it's just that they're not as good. And so, the other reason you're going to be putting, and over here I have a fucking mess, so I'm just going to show you the answer key, but you guys got the idea, which is what matters. On the one hand, we have extrapolation. On the other hand, is that you cannot, at least not always reliably, make a prediction of x from a value of y. So, in other words, it's what I mentioned. If you plug in y equals 15 Celsius, in order to get an x, it's not as reliable as plugging in 2000 for x and trying to get a y. Okay, and this is just the nature of math. It's easier to get your dependent variable through your independent one. See? It's easier to plug in x and get a y than through the y get an x. See? Another way I can sort of make this reach you if you're still like, what the hell, what's going on? We talk a lot about how a function is like a box. See? It's like a machine. It's like you plug in an x into your function. Here's the black box. And you get a y value. See? You're supposed to plug in x and get a y. And so doing it the other way around, the box was not really made for that. Does it work? Yeah, it can work, but, and here's the main point, it's not always reliable to do that. You might encounter some problems that I'm not going to get into because this video is probably way too long already, but it's not always reliable. It's not what you're supposed to do. The main idea here and the main thing you have to notice is that you are trying to find x through a y. That should ring a big red flag. Ladies and gentlemen, that is G, and that is for number 1. Alright, you guys, so for this second one, we have that we need to consider the function f of x equals 3x minus 1 plus 4x to the power of negative 2. Okay? Part of the graph of y equals f of x, which is basically just, our graph, right, is shown below. And so it has this part where it goes all the way up. Then there's a little bit of space in between. There's something going on here, right? There's a little bit of space in between. Then it sort of like comes back with a curve. There's something here. And that is my graph. See? All right, cool. So the function is defined for all values of x except for x equals a, and to write down the value of a. All right, so intuitively, what I just told you that over here, right, it sort of like disappears. Well, that would be where the function is indefined, right? Because it tells us that the function is defined for all values of x, so all these values of x are legal, except for when x equals a, which is somewhere around here. See? We're not sure where, but it's somewhere around there. When a function is undefined, that means that the value of x that you're putting in is not legal. Okay? When something is undefined, you're putting in a value of x that is not legal. It breaks some math rule, you know, and it can be a lot of different things. Okay, so let's go piece by piece. Let's write down f of x. F of x equals 3x minus 1 plus 4x to the power of negative 2. And so apparently this function is undefined at some point. When x equals a, it is undefined. See? So when x equals a, we have something that is undefined. Now, let's look at the nature of this function and see where my values might get undefined. And so piece by piece, I'm going to prefer, and this is a personal thing, to put the negative 2 in front. See, so I'd rather have, just reorganizing a little bit, f of x equals 4x to the power of negative 2 plus 3x minus 1. Okay, so that way I have the 2 in front. And what does the negative exponent do? What does the negative exponent do? What it does intuitively is that you are technically going to flip it. And so a negative exponent means that you flip it. So never ever forget that. You flip it with a negative exponent, okay? And so what do I flip exactly? Well, this negative exponent is affecting what? Is it affecting the 4? Is it affecting the x? Is it affecting this 3? Ladies and gentlemen, it is only affecting this x right there. That means that if I apply the negative exponent, what do? I flip it. Okay. So do a backflip. 4 divided by x to the power of 2. So you flip it, and then it goes positive? No, 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 no. You flip it, and you multiply by negative 1. You flip it, and you multiply by negative 1. You flip it, you multiply by negative 1. Let's leave that super duper clear. So if you have x to the power of negative 2, you flip it, so it ends up on the bottom, right? And you multiply the top, the negative 2, times that negative 1, right? And that means you end up with 1 divided by x squared. Why is it useful to understand it this way? Because the day of tomorrow, you might have something that looks like this. 1 divided by x to the power of negative 3. So if you want to flip it, well, now it's going to go on top. And you need to do the negative exponent thing. Multiply by negative 1, so you don't forget. It goes positive. And so very intuitively, you can kind of think that like flip and change symbol. Ooga booga. Flip, change symbol. All right. That means if you have x squared, which is something that you would probably want, but just so that we're on the same page, if you have x squared, you can flip it and multiply it by a negative 1. So you can actually rewrite x squared as 1 divided by x to the power of negative 2. All right. That is all you need to know for negative exponents. See? Yeah, whatever. So this negative exponent makes this happen. So now I have 4 divided by x squared plus 3x minus 1. All right, and so now we need to see what makes this function be undefined. And so whenever they're asking for an asymptote, which is something that shows up later, see? You gotta think about what undefines my function, okay? Or when they're talking about domain and range, think about what limits my function, which is sort of like what undefines it as well, okay? So I used a lot of buzzwords right now, and I'm sure at least one of you is thinking, what the fuck? I know I've heard of asymptote, but I forgot what it was. What is domain? What is range? Which one was X? Which one was Y? All right, guys. Domain and range are the values that X can take in domain and the values that Y can take in range. Literally X and Y, okay? And so domain are the values that X can take. Range are the values that Y can take. This can be limited by stuff that your function has, okay? An asymptote is something that is never touched. So for example, if I have, let's say, something that looks like this, okay, just whatever, I don't know, and we can do something like this, okay. So if I have a function that looks like this, and over here we have, I don't know, 1, ¿cierto? That is a 1. Then I can say I have a horizontal asymptote. Horizontal asymptote at y equals 1. See? Because at y equals 1, x is never going to touch that value. See? You can also say you have a vertical asymptote. Vertical asymptote maybe at x equals 0 because your value of x will never touch right here. See? X equals 0, y equals 1. So that is the intuition of asymptotes. That is just a quick, like 101, see? And so when you look at this function, well, what is special about this function? Of course, what's special about this function is the negative exponent. What did the negative exponent do? It made my x be on the bottom. It made it be on the bottom in what is called the denominator, see? And so you have numerator on top, you have denominator on the bottom. When you have an x on the bottom, you have to be careful because x cannot equal 0. Why can x not equal 0? Because you cannot divide by 0. Ladies and gentlemen, 0 divided by 3 is how much? 0. 3 divided by 0 is how much? It's undefined. Quite literally, it is undefined. And if you're not sure or you don't remember and you're in the middle of the test and you're like, fuck, there's an x in my denominator, but I don't recall if it was dividing by 0 on the bottom or on top. Just put in your calculator. Who gives a shit? So 0 divided by 3 gives you 0. 3 divided by 0 gives you error. Divide by 0. Undefined. You cannot divide by 0, guys. Okay, it is that simple. So here, I identify that x cannot equal 0. And what value of x made it undefined? Well, we just found out that x equals 0 makes it undefined. So that was a little bit of a long introduction to this exercise, but I think that's fine. A equals 0 because x cannot equal 0. See, you can understand it this way if you'd like. X cannot equal 0, so what undefines it? A equaling 0. See? It's the same idea. All right, so that is part A. Part B, we need to use your graphic display calculator to find the coordinates of the local minimum. And so there's two very important buzzwords here. On the one hand, you have local. On the other hand, you have minimum. And so what is going on there? See, imagine we have a function that looks a little bit like this. You have something that goes, I don't know, whatever. Just, oops. Let me try that again. So you have something that goes a little bit like this. See? And let's say that here your function dies. Like this is where it starts, this is where it ends, period. Okay? Here you have x, here you have y. And so, guys, take a moment and look and point out for me, please point out for me the maximums. And so you take a moment, you look and you say, okay, so I have a maximum here, you have a maximum here, here, here. And so all the maximums are in orange, okay? Now, maximums can be defined, maximums and minimums can be defined in two ways. You have what they call the local, which is what shows up in this exercise, and you have the global. And so following that intuition, I think it's easier if we start with the idea of the global. So the global maximum is going to be the biggest maximum. And so what is the biggest maximum? The biggest maximum is going to be this guy here. And so if this is my global, then which ones are my local? Let's use this color here. So for local, we're going to have that this is local, this is local, this is local, this is local. So basically, all you really need to keep in mind is that the global is going to be the biggest maximum, or if we're talking about minimum, the smallest minimum, okay? And the local is just going to be all the other ones, okay? And so here I would actually have 1, 2, 3, 4, 5. So this is 5 minimums, where I have 4 local minimums and 1 global min. Okay? So that is intuition for local and global. This is for maximums. If I do the same exercise for, points out for me the minimums, it's going to be quite similar. I mean, we're going to have, whatever, let's just use this color here. So we're going to have that for minimums, we have this minimum, this minimum, this minimum, this minimum, this minimum. See? 1, 2, 3, 4, 5. Which one is the global minimum? It's this one. So this is going to be my global minimum. And my local minimums are going to be all the other ones. See? And so here, 1, 2, 3, 4, 5. I have 5 minimums, 1 global minimum, and 4 local minimums. Okay? Whatever. That's the idea of global and local. And so why do they ask for us for the local minimum? Because technically, this graph keeps on going. Okay? In both directions. And so the minimum is going to be your smallest value. And so yes, we're used to the minimum being like, I don't know, like right there. See? Why? Because we're talking about a quadratic that looks like this. Anytime there's a curve or a point of change, your minimum is going to be here or your maximum is going to be there. Okay, this is not new news for most of you probably. This is going to be the vertex, see? And your quadratic. And it's usually the vertex has the minimum or the maximum. See, on the left example we have a maximum, on the right example we have a minimum. See, and so for when they ask for a local minimum, it's like the one you see in this picture. Okay, because you might have a minimum over here that goes like that, but you don't see it. And so what's the local minimum? What's the minimum that they're seeing? It's the one that I have highlighted in yellow in my graph right now. Just to leave that idea very clear, what we see in this graph right now is something that goes along the lines of this and this. And so you know that there's a minimum there for sure. See? And so you can call this a local min. Now you don't know if this local min is the global min or it's just a local min, because this graph might keep going and it might keep going like this. See? And so this minimum would actually be like the global one, like the smaller one. All right, whatever. Enough blah blah. Point is, there's more than one minimum. You know that this is a local minimum because it's one that you're seeing. Okay? Fuck it. Here's a local minimum. How the hell do you find it? Because we can use our graphing calculator, what you do is you go ahead and graph and then use functions in your graph to find the minimum. Okay? There are other ways to do it, but I'm going to show you this way because it's a little more direct. Okay? It might take more time, but it's more reliable. And I'd rather show you the reliable way. So you open up your graphing calculator, you go to y equals. Okay, so the point of y equals is that you can plug in functions and then play around with them. So I'm going to put 3x minus 1 plus 4x to the power of negative 2. All right, double check that it's all okay. Go ahead and graph. And so probably you are right now graphing and you're having the same issue as me. Nothing shows up. Nothing shows up, not because you put in your stuff wrong, but because the window is wrong. Okay, maybe you're too zoomed out, maybe you're too zoomed in, maybe you're looking at the wrong area. So what you can do is, what I suggest actually is first start by pressing zoom, go all the way down to what is called zoom fit. Sometimes zoom fit helps you find like the points of it, like the important points, like intersect, min, max, whatever. And so here I did a zoom fit, and as you can see, I can see a little bit more of the nature of the graph, but the dimensions are still a little bit fucked up. And so what you can do is go into window and start playing around until it looks nice. For example, this Y max of 350 is probably making it look like shit. Now, a quick tip, see? If you're not sure what values to put here, well, sometimes they give you values. So I'm going to put a minimum of x equals negative 4, a maximum of x equals 6, a minimum of x equals negative 8. That means y equals negative 8, and a maximum of y equals, this is probably, yeah, this is 14, so y equals 14. And so there, just like that, whoops, I can go back here and put, okay, minimum negative 4, maximum 6, Y min is going to be -8. And this one's going to be 14. All right, and just a nerd sort of moment, but the SCL, okay, so see how you have X SCL and Y SCL? That is by how much it sort of changes. What I mean by this, if you go ahead and graph now, see how each of these have like those little sticks going around, like this part of the graph? So those sticks, okay, the X SCL shows you how much distance is between each of these. And so if right now my X equals 1 for SCL, X SCL equals 1, that means from here to here it's 1. From here to here it's 2. I mean, sorry. Each of these is 1 point of distance. That's what I mean. If you change your X SCL to, I don't know, 2, that means each of these jumps is going to be a distance of 2. As you can see, all that really helps with is sometimes making your graph look nice. Okay, it doesn't aid you in finding the intersect quicker or whatever. No one gives a fuck. Okay, as long as you can see it, that's all that matters. I just thought I'd share that so that you know what it is. Okay, don't ever change it, just leave it on 1. So now I have my graph, and now I need to use my graphing calculator to find the minimum. So because we are trying to calculate something, we can go ahead and press the calculate button that is on top of trace. So you press second, trace, you hit calculate. So here you have a lot of fucking tools. You can find some random value, you can find zeros, minimum, maximum, intersect, etc. See? Obviously we're trying to find the minimum. So we press minimum, what does it ask for? It asks for left bound. Later on it asks for right bound. And so if I go ahead and put, I don't know, left bound here, and right bound there. What I'm basically doing, just so that we understand, okay, what I'm basically doing is that if I put, say, if I put the left bound here, so left bound, and I put the right bound here, well, then the last part is guess, which is basically like pick your minimum. So I'm going to pick here. What this does is that your calculator goes ahead and scans this area from the left bound to the right bound. It sees which minimums it finds, and it uses what you guessed for to pick that minimum. Why is that important? Because let's say over here you do, I don't know, this is your left bound, okay, and this is your right bound, and I say, nice, scan for minimums. It's going to scan all of this, and how many minimums is it going to find? It's, whoops, I don't know what's happening. Okay. It's going to find 2 minimums, right? It's going to find this one and this one. Well, maybe this one, see? And so this is where your guess function comes in and helps you pick one or the other, okay? That is why it asks for left bound, right bound. It's just helping you tell your calculator where to scan. And the guess thing is for you to pick a minimum if there's more than one. In this case, we can guess fucking anywhere because it only picks up on 1. Okay, well, apparently I need to guess within the bound. Big fucking deal. So left bound over here. Right bound over here. And I just guess anywhere within the bound, apparently. It's going to find the one I need because it's scanning in the right area. That is my minimum, see? And so the local minimum we're going to write is following this. Give me one moment. Yeah, so we can put 1.38672 and 5.24025. Then suddenly for this next part, they tell us that the equation f of x equals w, where x is part of all real numbers, has 3 solutions. Identify one possible value for w. Alright, so this part is definitely pretty weird, and you need to understand some conceptual stuff, I guess, in order to solve this, see? And so, let's go piece by piece, see? First of all, you might be reading that and thinking, what the hell, I don't get it. Okay, and that's where I tell you, guys, a lot of times in the IB, and I'd say especially for paper 2 actually, I'm going to go on a limb here and say especially for paper 2, usually like what you need for part C is something you did in part B. What you need for part B is something you did in part A. Why is this useful to know? Because it can be a massive hint for how you answer the next part. Okay. Um, it's not always the case, but consider it because it can be a massive hint. So the equation of f of x equals w. Okay, so that means I equal this to like a w, and I can have three solutions. Okay, so f of x equals w. Let's understand something right off the bat. See? So f of x equals w. Actually, well, let me start in a different way. So let's say you have f of x equals, I don't know, 3x plus 2. See? Just a random ass function. I'm just trying to explain the following idea. F of x is a very fancy way to say what? F of x is the fanciest way you will ever meet of saying y. So f of x equals 3x plus 2 is the same as if I told you y equals 3x plus 2. Alright, so why do mathematicians use f of x? Because then you can keep good track of what you're plugging in for x. For example, f of 2 is basically you asking your function, what is y when x equals 2? And that is why f of 2, what you do is that you plug in this 2 into this x, and you end up with 3 to the times 2 plus 2. In other words, 6 plus 2, in other words, 8. So f of 2 equals 8. See? All right, so that is sort of the intuition of what is f of x. See, f of x is basically just y. And so what's going on here, they're telling me that when f of x is w, so basically, for some value of y, where it is part of all real numbers, okay, this is just a fancy way to say it's part of all real numbers, which is like all numbers really, okay. So for some value of y, this equation has three solutions. Okay, now it's a little bit more friendly. For some value for y. Okay. Let's say I have a y of 2. A y of 2, all right, a y equals 2 is where? It's right here. So a y of 2 goes like this. How many solutions does y equals 2 have? All right, I know that some of you are like, brother, what the heck are you doing? If y equals 2 and you draw this horizontal line because we're talking about y equals 2, ¿cierto? Where does it touch my function? Ah, it touches my function here. So how many solutions does it have? It has one solution. Why is this important to know? Because let's say you are solving a parabola, ¿cierto? Something that looks a little bit like this. And they ask you to find the famous zeros. Okay, the famous zeros are wherever your function touches at x equals 0. Which in other words is the same as finding your x-intercepts. Okay? So what you're technically doing is that much how we just did y equals 2 and found two solutions, right? When you find zeros, you are drawing a line through y equals 0 and seeing where you cut x. All right, so small mistake here. I did not mean x equals 0. I retract myself. For the x-intercept, you find y equals 0. For the y-intercept, you find x equals 0. Sorry about that, small detail, but whatever. Point is, this thing of like drawing a line and finding the solutions, you've been doing it all along. You know, you've been doing it for the quadratic function. That is actually why you equal your function to 0 when finding, I don't know, the zeros of x squared plus 2x plus 1. You equal it to 0 because it forces you to do this two solutions thing by drawing a line, okay? All right, cool. Why is that useful? Because if I go back over here, so at y equals 2, I have one solution because it touches only once. Okay, so where does it touch 3 times? Where do I have 3 solutions? Where does it touch 3 times? At y equals 4, it still touches only once. At y equals 5, it still touches only once. At my minimum, ooh la la, at my minimum, it touches here and here. So here it touches 2 times at my minimum. And the moment I go a little bit above my minimum, just a little bit, right above, for example, there, it touches how many times, ladies and gentlemen? Bada bim, bada boom, it touches 3 times. And so anything above your minimum is going to have 3 solutions. All right? So one possible value for W, well, you can just, I don't know, you can put like y equals 12 and it's going to work. See? I mean, sorry, W equals 12. It's going to work. It's going to give you those 3. See? If you're not very convinced that that's going to get you a point, you can be very rigorous and just put like any value greater than my minimum, and then make sure you put greater than and put the value of your minimum to show your work, 5.24025. So that would be for part C. And notice how for part C we needed something from part B. So the minimum was relevant because that 5.24025 came from part B. See? All right, let's keep going. They tell us that the line y equals mx minus 1 over 4 is tangent, keyword, tangent to f of x when x equals negative 4. Write down whether the value of m is positive or negative. Justify your answer. So here we need to clarify a little bit. What is even a tangent? Okay, once we have that keyword ingrained in our brains, the intuition and everything, finding it, the answer to this next question, is actually very easy. And so a tangent, you guys make memory, is something that touches your line once and then never again. For example, let's say I draw a quadratic again that looks something like this. Let's say that I have a tangent at, I don't know, x equals 2. And so at x equals 2, which is around here, I have a tangent. That means it's a line that touches once at x equals 2. At x equals 2, it touches once and then never again. So this would be a tangent at x equals 2. Why is this relevant? Because sometimes it can help you find certain slopes or whatever. For example, if you force this tangent to have a slope of 0, if your tangent has a slope of 0, what this can actually help you do is find what we call the minimum. Why does it work that way? Because the slope of this guy here is, I don't know, it's positive, right? It's like 3, it's going up. The positive of this guy here is, I don't know, negative 4, whatever, I don't know, see? But as you get nearer and nearer the minimum, the slope actually grows. And so here's the slope of negative 4, here's the slope of negative 3, here's a slope of, I don't know, negative 2, and eventually you're going to find a slope of 0. A slope of 0 is a horizontal line. Completely horizontal line. Here you have a slope of 0. And so if you make a slope of 0, it can help you find the minimum point, the vertex. See? All right, that was like a nerd moment, but just so you know, usually when you find the derivative, which helps you find slope, you just equal it to 0. Why? Because it helps you find a minimum or maximum. Okay, cool. So that we have a tangent when x equals negative 4. So first things first, let's not complicate ourselves. Where the hell is x equals negative 4? X equals negative 4 is here. So then it goes all the way down. See? So probably it's probably something that is just going up. See? So there's not much we have to be scared about. You can probably just put, looking at the graph, it has to be positive. See? Now I know that some of you are not very comfortable with that, but I am going to tell you right away that if you look at the answer key, that is literally a way to answer. You can say, the function is increasing at x equals negative 4, so the slope has to be positive. See? And so you can conclude that just by looking at it. I mean, literally, you can conclude that by looking at it. It's what's likely, whatever. See? Now, let's get a little bit more scientific because It's not the idea to do things eyeballing it, see? So at x equals -4, is it growing or not? Let's find a way to sort of prove it, see? So if I have my function here and my y equals, let's see what value of y I get for x equals -4. So what I can do is I can go to table. So press second and then graph to hit table. So when x is 4, y is 11. Now notice, what's the relationship? So, well, eventually when you reach 0, you get the error undefined, right? But as you can see from 1 and above, so 1 is around 6, 2 is around 6, on 3 it starts growing, on 4 it starts growing, on 5 it starts growing, 6 it's growing, 7 is growing. So there it's definitely growing, see? It's not some sort of point where like it grows then stops growing or shit like that. No, it's growing, it's increasing. And so what we can say is that because it's increasing, then your tangent has a positive slope. What is m in this context? It is slope. Okay, so y equals mx plus b. What's the intuition? This is your y-intercept. This is your slope. And so when x equals -4, it is definitely going to be growing somewhere down here, ¿cierto? But it's going to be growing. It needs to have a positive slope. See? So m has to be positive. Justification of my answer, function is increasing. Function is increasing at x equals -4. See? And how did you prove it or find out? By looking at the table. See? So yes, we eyeballed it a little bit intuitively, but then we checked with the table and it is correct. So function is increasing at x equals -4. This is one point. The other point comes by saying that the slope has to be positive. See? All right, cool. So now we also learned a little bit what tangent is. So that's nice. All right. Then they give us that a second function, ooh la la, is given by g of x equals k times p to the power of x minus 9, where p is greater than 0. The graph of y equals g of x intersects the y-axis at the point this and passes through the point this. With all of that, we need to find the value of k and p. Guys, I'm going to say right away, like this right here could totally be like a question for paper 1, okay? So this right here doesn't have much to do with parts A, B, C, and D. Well, the last part does, okay, like part H and G. But this by itself is like its own exercise, okay? Why am I pointing this out? Because the day of the exam, you might not know how to do A, B, and C, and D, but you will know how to do E, see? I know that I said earlier that part B has to do something with part A and etc., but it's not always the case, okay? And I know that's a weird tip or trick because I'm not telling you that it's always the case, so it's not a rule of thumb you can use, but it is something you can consider. If you look at an exercise and the first 3 parts you're like, fuck, I have no idea, get points where you can. Look at part E, look at part F, look at the last question. Maybe there's something you can do, okay? Get points where you can, don't give up. That's my message. So, what is the value of K? What is the value of P? So, we gotta go piece by piece. The key information that they give you, okay, is the value of A, which is a point, and a value of B, which is another point. So, let me explain this very, very intuitively. Let me go ahead and zoom in a lot. So, I told you guys that g of x, or f of x, is the same as y. So let me rewrite this and say that y equals kp to the power of x minus 9. Now, which variables do I have here? How many? I have one variable, I have another variable, I have a third variable, and I have a fourth variable. And so right now, it's very hard to solve this because there is more than one variable. Okay, that is the idea that I'm trying to share. The moment you have more than one variable, it's hella hard to solve. See? So let me go back, write this again. So right now I have 4 variables, and it's hard to get one of them alone. See? It's hard for me to end up with, I don't know, y equals 2 because there's 4 fucking variables. It's gonna end up as y equals 2 plus k times p and like x is somewhere. See, so point is there's a lot of fucking variables. You need to find a way to get rid of some of them. And so this is why they give you points. For example, if I go ahead and plug in this point A, and I know I can plug it in because they tell me that the y-axis is at point A, so it's part of the function. See, I'm not plugging anything in. I'm plugging in a specific value that is in my function, so it is legal. It's going to work. If I go ahead and plug that in, well, my x is going to be 0, my y is going to be negative 5. So negative 5 equals k times p to the power of 0 minus 9. Now, something to the power of 0 equals what? Anything to the power of 0 equals 1. And so negative 5 equals k times 1 minus 9. Negative 5 equals k minus 9. Ladies and gentlemen, I just passed from 4 variables to 1, which is amazing because now I can solve for k and I end up with, well, plus 9 plus 9. K has to equal 4. So notice how the intuition is, okay, you have a lot of variables, how you can get rid of some of them. Usually just by plugging in some points, it is something that you can figure out. So now I have k equals 4, which means that in my original exercise, I now pass from having 4 variables to having 3 variables. So now I'm a lot more happy, see? What does that mean when I plug in this point here? This 3 variables is going to go to minus 2 variables, I end up with just 1 variable, which is what we want. All right. Just want to mention that so you understand the way of thinking, the intuition, the etc. See? So k equals 4. That is going to be this part here. So k equals 4. All right. I know some of you are probably still thinking or a little stuck on why the hell, whoops, why the hell something to the power of 0, okay, is equal to 1. So just a quick sort of like demonstration, see? The study of math is often considered the study of patterns. See, it's filled with patterns all over the place. And so if you go ahead and I ask you, yo, what is 2 to the power of 3? You're going to tell me 8. Now, how do you know that it's 8? You know that it's 8 because it's 2 times 2 times 2. So 2 times 2 gives you 4, times 2 gives you 8. See? 2 to the power of 2 is what? 2 to the power of 2 is awfully similar. It is just 2 times 2. It is 4. And 2 to the power of 1 is just 2. It's just 2. And 2 to the power of 0, well, this guy online says it has to be 1. So 2 to the power of 0 equals 1. All right. There's like 2 ways you can think of this, okay? The first way is that technically all of these different scenarios that I just put in front of you have a times 1. Why is it useful to think about it this way? Because then this 1 tells you how many 2's show up. So, if 1 2 shows up, then 2 times 1 gives you 2. If 2 2's shows up, then 2 times 2 times 1 gives you 4. If 3 2's show up, it's 2 times 2 times 2 times 1 gives you that 8. And if you work backwards, you see that, okay, so 2 to the power of 0 means I have 0 2's. I have just 1 1 equals 1. That is one way you can think of it. The cooler way, in my opinion, is that to go from here to here, you do what? You do times 2. To do from here to here, you do what? You do times 2. To go from here to here, you do what? Times 2. This is also useful if I go ahead and ask for 2 to the power of 4. Well, you just do this times 2. It's going to give you 16. Ah, okay. So, why is this useful to know? What if I ask you to go backwards from 16 to 8? What do? Well, what's the opposite of multiply? Divide. So 16 divided by 2 gives you 8. 8 divided by 2 gives you 4. 4 divided by 2 gives you 2. And 2, ladies and gentlemen, divided by 2 gives you 1. And so no matter if you do this with 3 squared, no matter if you do this with, I don't know, the world of 3 squared, ¿cierto? So it's going to be from 9 to 3 to 1. Here you divide by 3, see? And so notice how eventually, divide by 3. Eventually, you're going to end up with the number you're analyzing divided by itself. And so the number you're analyzing divided by itself will always give you 1. The number you're analyzing divided by itself is always going to give you 1. See? And so that is why that pattern happens. That is why it works that way. That is just a small explanation so that maybe you remember a little bit more why anything to the power of 0 is going to give you 1. Alright, fuck it. That is the value of k. See? So k equals 4, and now back to the game plan. Right now I have 3 variables. I want to have just 1. So if I plug in the point b, well, x is going to be 3, y is going to be 4.5. So 4.5 equals 4 times p, which we said was, whoa, times p, which we still don't find, to the power of 3 minus 9. And so if I get these values alone, I can do plus 9 plus 9. We end up with 4p to the power of 3 equals, well, 4.5, 4.5 plus 9, 13.5. I can keep getting p alone by dividing by 4. So that means that p cubed equals 13.5 divided by 4, 3.375. And so from here, in order to get rid of this square root, I can do this square root with a 3 hidden in there. Y with the 3 hidden in there because this goes away with this. And so p equals the square root with a little 3 in front of this. How do you put the little 3 in front in your calculator? Well, there's a lot in the math button. So you go ahead and press math. There's a lot of shit over here. And it's going to be number 4. So number 4 gives you what we're looking for. If you ever end up with a bigger sort of number you have to do, you can go ahead and put, let me try again. You can put this 5th option, and you can change, whatever, you can change here, see? You can make this 5, you can make it to 7, etc. Just so that you guys know, technically, the default, for example, you have, I don't know, x squared equals 4, see? So you want to get x alone, you do square root, x equals square root of 4. Notice how there's no little number here. Well, there actually is. There's always a little 2, okay? The special scenarios is when that little 2 changes to something else. Why is there a little 2? What is the intuition of this? This little 2, what is it is asking you is one number multiplied by itself twice gives you 4. Which is why, for example, x to the power of 3 equals, I don't know, give me a moment, 8. If I do this square root here, and I gotta put it 3 to get rid of this with this, see? What I'm asking it now is what value multiplied by itself 3 times gives me 8, which as we know is gonna be 2, because 2 times 2 times 2 gives me 8. Whatever, guys, it's just intuition that this little number, okay, is how many times you multiply it by itself, see? And so the default, which is why you don't write it, is 2. So here it's not the default, it's 3. So, did I do it already? I did not. So math, put this 3, get 3.375. There is my value of p. So p is going to equal 1.5. All right, we did a lot of sort of review there, but I think for some of you it helps out a lot. So there it is. All right, let's keep going. For part F, what is the buzzword? Write down the equation of the horizontal asymptote of y equals g of x. What the hell did I just read? So, blah, blah, blah. Yeah, horizontal asymptote. Guys, I told you earlier that an asymptote is a number that, or a value that your function can never take. Let me write that again. a value that your function can never take. See, for the asymptote. The thing is, you can have horizontal asymptotes or vertical asymptotes. See, usually for the vertical one, you can just find. Ah, fuck. I can't. Here's the thing. So, if you have a vertical asymptote like the one we just saw, which was at, I don't know, like x equals 0, see? So that means for vertical, you have an x value that it cannot be, see? For horizontal, it's a y value that it cannot be, okay? And so usually for the vertical, see, for the x value, you can just look at what undefines it and then you can figure it out, see? For the horizontal, it's not so easy. It's not so direct of just finding like, oh, where you divide by 0 or where your function doesn't make sense because it gets undefined. It's not as direct, see? And so usually what you need to do is graph it, okay? Or at least that's what I suggest. It's the easiest way, in my opinion, right? Whatever. And so basically, there is an equation of the horizontal asymptote of this equation, g of x. Now, g of x, what is it? Well, I already found k, I already found p. G of x, in a more fancy way, is going to be 4 times 1.5 to the power of x minus 9. So if I go ahead and graph that in my graphing calculator, we end up with 4 times 1.5 to the power of x. Sorry. And then I can graph it. So here, most of it shows up, but I don't really see the asymptote. So I can go ahead and do zoom fit to try to see if my window nails it more quickly. Here I get a bigger sort of function. All right, so now I'm starting to get the idea of where the asymptote might be. And so I have some sort of function that looks a little bit like this, see? And so there has to be a horizontal asymptote right here. The thing is, right now I don't see it, right? So what I can do is I can zoom out a shit ton. So you can either press zoom, zoom out, or you can just change the window. See? I'm just going to change the window, like, to each their own. See? So negative. I'm just going to be very exaggerated so I can see the answer right away. So negative 400. We're going to leave the same x max. Or actually, 50, just so that it looks a little bit more pretty. Okay, clearly I zoomed out too much. Gotta take a chill pill sometimes. Let's put negative 40, max 15, and a bigger y minimum. So y, I don't know, negative 25. Yeah, graph. Okay, now it's very apparent where my horizontal asymptote is. See, so clearly that is the value that I cannot take. Now, how do you find it? Well, that's the thing. Use your graphing calculator. What I suggest is go, actually you can go trace. So this trace button, what it does is that you can move along your function and it gives you each and every value of each point. So for example, right there, x is negative 10, y is negative 8.9. See? So if I go a little bit more to the right, this point here is 3.88 for x and 10 for y. See, it makes sense because positive y, positive x, there it is. See? So how can this help you find the asymptote? Well, go to the part where your values sort of like get stuck. See? And so if you go all the way to the left, easy question, guys. What is the value of y that it never seems to touch? It's 9. It's negative 9. I mean, look at that. It's y equals negative 8.999999999. It's a lot of no's, you know? So, y can never equal negative 9 just by graphing it and looking at it. Yes, that is good enough. Seriously. So, for part F, the equation of the horizontal asymptote, very important, is going to be y equals negative 9. So the way you can think about it is that the equation of the horizontal asymptote is y equals negative 9. And in your function g of x, in g of x, y can never equal 9. And so the equation of the horizontal asymptote is exactly y equals 9. See? Notice that is important. One thing is the equation, one thing is what g of x can never be. So g of x can never have y equals -9. There's a negative missing there. So g of x can never equal -9 for y. And so your equation of that horizontal asymptote is exactly at y equals -9. See? That is a small sort of thing you have to get in your brain because it is part of how you're supposed to answer. For example, here they tell you for the horizontal asymptote, you write y equals -9. See, that is the equation. That you actually get negative points if you put g of x equals -9. See? Gx can never equal -9. Technically, you can write it like this, and then this implies that your equation is at y equals -9. See? That is the more clear sort of explanation. All right, whatever. So, that is g. And then the third function, h. Oh, wait, fuck. That is f, that is not g. So for g, they tell us to find the solution of f of x equals g of x when x is greater than 0. And so, go piece by piece. Right now, we need to find the solution of f of x equals g of x. So let's go ahead and write that over here. F of x equals g of x. Now, what is f of x? What is g of x? We know that f of x from this exercise up top is this. So f of x is going to be 3x minus 1 plus 4x to the power of -2. We know that g of x for part E is going to be this guy here. See? So g of x is 4 times 1.5 to the power of x minus 9. And so here we need to find find the solution when x is greater than 0. See? So some of you are probably looking at this thinking, damn, how the hell do I figure this out? See? And so what I suggest, you guys, the main tool, and I have a video on this but I'm going to do it detailed here anyways, is the calc intersect trick. Actually, go ahead and put it up here. So the calc intersect trick. What the calc intersect trick does is that it helps you find the intersect or where it equals one equation to another. So if you call all of this y1, if you call all of this y2, and then you do calc intersect, you're going to find exactly the value of x that makes these things equal each other. Literally. And so, but let's understand a little bit why, okay? So if you go to y equals, well, actually, we're going to switch this around just because it's already ready. So this is going to be y1, this is going to be y2, okay? So this is y1, y2 is going to be this, so 3x minus 1 plus 4x to the power of -2. If you go ahead and graph this, double check that you plugged in right. If you go ahead and graph this, see? Okay, so the solution of x, let me zoom in a little bit more, or let me do zoom fit to see if I can find the intersects. Alright, as you can see, sometimes zoom fit doesn't help as much as we'd like it to. Yep. Let me change the window a little bit. So y min, let's make this, I don't know, -10. Y max is fucking huge for some reason. Nice. This will look a little better probably. Alright, so there's my equation or function with the asymptote. And there is my other one. And so, just to be mega clear now, let me make an even smaller x min. Yeah, so this is what we're dealing with. We're going to work with this graph here. And so basically, we need to find the intersection of these 2 points. We need to find the value of x that solve this. And so right now, where are my x-intercepts? I have two. I have one down here, and I have one up there. And so what we can do is we can go second calc for the calc intersect. And here it asks for the first curve. Usually picks it out pretty easily. So this is my first curve. And then the second curve is over there. See? Then we have guess. So guess helps you pick your intersect. Now they are asking for which one? They're asking for when x is greater than 0. And so that is why some people maybe they go to guess over on the other side and they do find an intersect. They're not wrong. It is an intersect, but it's the wrong intersect. Actually, in the answer key it says like you get 1 point for process and 1, but no point for the right answer. See? Yes, you did the calc intersect correctly, but this intersects here at negative 2.39 is the wrong one. Literally, it's the wrong one. All right? And so go ahead, do calc intersect. Make sure you're on the positive side. Okay? Make sure you're on the positive side. Guess over there. Here is your intersect that you're looking for. It is at 4, comma, blah, 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 11.25. See? So this is the point of my solution, and the solution itself is the value of x. Okay, so the value of x is going to be x equals 4. That is for part G. All right, and h, we're almost done. We need to consider a third function, h, where h is the sum of both functions, f of x and g of x. That tells us that point C, which is negative 1 comma q, lies on the graph of g of x. We need to state whether C also lies on the graph of h of x. So, piece by piece, what is point C? And so point C, they tell us that it's an x of negative 1 and the y of q. Okay, y of q doesn't really help, so let's find out what q is. And so this point lies on the graph of g of x. So what was g of x? G of x, we have it right here, see? So let's go ahead and plug in negative 1 for g of x and see what I get. And so if I go ahead and plug in negative 1 for g of x, I'm going to have 4 times 1.5 to the power of negative 1 minus 9. All right, so technically, from what I just found here, I have that the point C, okay, point C is negative 1, comma negative 6.33, never ending, see? And so now we need to see if this point also lies on the graph of h of x. Now what is h of x? H of x is f of x plus g of x. So h of x is f of x plus g of x, which is the same as me saying that h of x is, well, f of x, ¿cierto? So it's going to be 3x minus 1 plus 4x to the power of negative 2. So that is this here. Plus g of x, which is 4 times 1.5 to the power of x minus 9. That is g of x. And so this whole thing is h of x. Now, what we can do from here, okay, is see if point C exists, if it makes sense. If it makes sense, plugging in point C should give me a value in h of x that makes sense, okay? In other words, I can go ahead and plug in, so point C was what value for x? It was negative 1. So if I go ahead and plug in negative 1 for h, I'm going to have negative 1 here, right? So it's going to be 3 times the negative 1 minus 1, see? Plus 4 to the power of negative 1 to the power of negative 2. I mean, 4 times negative 1 to the power of negative 2. Plus 4 times 1.5 to the power of negative 1 minus 9. And so if all of this equals negative 6.33, then point C exists. If it doesn't equal negative 6.33, then h of negative 1 gives me a different point. See? Let's see what happens. Let's figure it out. So 3 times negative 1 minus 1 plus 4 to the power, times negative 1. I keep messing that up. To the power of negative 2 plus 4 times 1.5 to the power of negative 1. That is not a negative 1. Now it's a negative 1 minus 9. Now I just plugged in a bunch of shit, so let me double check. We all make mistakes. So 3 times negative 1 minus 1 plus 4 times negative 1, blah, 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 blah. No one cares, blah, blah, blah. Okay, cool. So when h is -1, this does equal -6.33, and that is a way in which we can say that c also lies on the graph of h of x. What is the justification of my answer? The justification of my answer is that h to the power of -1 equals -6.33. And that, part of my analysis, g to the power of -1, point c, ¿cierto? Gives you -6.33, which is the same as saying that q equals -6.33. All right? So ladies and gentlemen, that is how we solve h, and that is actually all of number 2. I extended myself a little bit in some parts, but you know what? I think it was pretty good review, and I'm sure at least one of you out there appreciated it, and whoever that is, this one's for you. So, ladies and gentlemen, I hope it helped. I hope you feel better. That is for number 2. All right, so for this third one, it's not that hard, but it is very specific. So, we have that the depth of water, W meters, in a particular harbor can be modeled by the function WT equals blah blah blah, where T is the length of time in minutes after 6 o'clock. Interesting. It's in minutes and it's after 6 o'clock. On the 20th of January, the first high tide occurs at 6, at which time the depth of the water is 18 meters. So here is an important piece of information. Then they tell us that the following low tide, okay, so let's use a different color. The following low tide occurs at 12:15 when the depth of the water is 4. This is shown in the diagram. So for example, the thing in yellow, that the high tide occurs at 6, at which the time of depth of water is 18. Well, this whole diagram is time in minutes after 6. After 6. So for example, at t equals 0, what time is it? At t equals 0, it's right at 6. Because this diagram is minutes after 6. And so 0 minutes after 6 is at 6. T equals 1 would mean I'm talking about 6:01. So that being said, this thing in yellow over here, right, we're going to have, over here we're going to have the point 0, comma, 18. So 0 minutes after 6, the depth of the water is 18 meters. All right? So that is the first piece of information that gets shared with us. And then it tells us that the low tide occurs at 12:15 when the depth of the water is 4 meters. And so that means that at 12:15, which is when the low tide occurs, so it's this lower point over here, right? We're going to have a height of 4. And so, well, what x value is this, right? Because my x is time, right? And we're talking about the low tide occurs at 12:15. Well, from 6 to 12, how much time passes? How many minutes? Well, it's easy to see, after you take a moment, that it's a 6 hours, right? Because there you reach 12, and then you add 15 minutes. But we want it all in minutes, because those are the units we're working for t, right? And so time in minutes, well, you take that 60, you take that 6 hours, you multiply it by 60, so 6 hours multiplied by 60, these are the hours portion, and then you do those plus 15 minutes. And so you have 375, so this point right here is 375 minutes, 4 meters. All right? Notice how we haven't even started the exercise, but already our diagram looks a little more friendly than what maybe it should look like. See? So that is something, a good habit to do. Make sure that your diagram has everything like written on it that it says. See? Or try to get all the juice out of what they're giving you. See, that's basically what I'm trying to say. So there we go. For part A, we need to find the value of A. And now here's what I meant earlier, that this exercise is not that hard, but it is awfully specific. Here we have what is called a cosine function. I mean, it literally says there, cosine, right? And so this cosine function, there are some specific properties or things about it you just kind of like need to know, okay? I know it's a little bit unfortunate that I put it that way, but I'd rather just be honest with you. This is not in the formula booklet. This is the kind of thing you just gotta learn, okay? So when you have this equation here, so WT equals A cosine BT plus D, there's a couple of things that we really need to understand. So first things first, this A, every time it's in front of the cosine multiplying, it's what we're going to call the amplitude. The other big important piece of information that we need to learn is that D, okay, D is the vertical, I'm pretty sure it's translation, okay? It's the vertical translation. And so depending on how A changes or how D changes, you have a cosine function that is slightly more different in specific ways. I know that didn't sound too specific, but let me just show you real quick what I'm talking about. So let's say I have this A, and then let's say that I have this being multiplied by cosine of, I don't know, x, and then I have our famous um, slider thing. See? So imagine that D like doesn't exist. See? Imagine that D is equal to 0. So this is like your starting point for the cosine, right? And so what the vertical translation does is that as it grows, your function literally goes up, okay? It doesn't change in any other way, but it goes up. For example, when it's equal to 2, notice how now sort of like the middle part of it, okay, where it cuts through the middle. What I mean by cuts through the middle, I mean this. When it cuts through the middle, is now up 2. But if it's up 1, now it cuts through 1. If it's in its starting point, how it comes from, it cuts through 0. And so that is a little bit what the vertical translation does, okay? And what the A does is the amplitude. So let's go from an A of 1 to an A of 10. What is happening here? Well, the waves still come at the same frequency, right? It's not like the waves are coming faster, but the waves are much bigger. And so with that in mind, we can understand a little bit better what amplitude is. Notice how value of A right now, well, from here, from the 0 all the way up here to the 10 is 10 because my A is 10. If my A is 11, now from the 0 all the way up there, it's going to be 11. All right, so that is just a little bit of a quick 101 on cosine stuff, right? And just to really have us all understand this a little bit better, let's say you have a cosine function that looks something like this. Okay, and there's a lot to it, but I'd rather just show you what you need, okay? Um, the amplitude, okay, is imagine you're cutting it in half, all right? The amplitude is always going to be from the middle to the top. So for example, this is one amplitude that you can also think about it as like from here to here. And this is also an amplitude, which is thinking like from here to here. So that is what the value of A does. The A is the amplitude, okay? And the vertical translation, well, it's a little bit like the orange line, but honestly, it's like, so it starts at 0, 0 like this, right? And the vertical translation makes it, I don't know, move up maybe like a whole unit, see? So you end up with that. That's what the vertical translation does, okay? B is this weird thing that has to do with period and this or that, but for this exercise, doesn't matter. I'm not gonna confuse you with more stuff. This is the cosine function, okay? So what can I do? For the value of A, well, what information do I have? I have these 2 points. So I have 0, 18, and I have 375,4. So let's go ahead and plug in both and see what happens. Okay, when in doubt, just plug in a point, see what happens. So if I plug in this first point, 0, 18, I end up with, let me just, yep, so this is my function. So if I go ahead and plug in 0, 18 here, you end up with 18 equals A times cosine, parentheses, B times 0. So T is equal to 0, right, in this point. And B times 0, anything times 0 equals 0. Anything times 0 equals 0, so I ended up with cosine 0. Now, what is cosine 0? Cosine 0 is 1. So this whole thing now turns into 1. So A times 1 plus D equals 18, which is the same as if I write A plus D equals 18. See? So this is the first sort of thing that we're going to obtain. And if I plug in the second point, that's 375,4, well, I end up with 4 equals A times cosine 375 times B plus D. And so this second one, well, neither of the two help me so much right now, because in the first one I have 2 variables, right? And in the second one I actually have 3. And so it's hard to solve it from here. It's hard to know what to do, but hey, we wrote our equations. This is what we have. We tried plugging in the points. We're not there yet. We gotta keep digging. See? So again, I'm just showing like the right procedure. Lay out all the information first, really understand what's going on, and then get playing. See? And so this is what I have. It's not enough. So the answer is going to be a little bit elsewhere. And this, again, apologies, it comes back to knowing really specific stuff about this specific problem, because you just gotta learn cosine and sine and all that stuff. See? So, remember how I said that these are the amplitudes? And that technically there's 2 of them, one that goes here, one that goes there. And well, this repeats all along, right? Well, technically, right, the amplitude can be expressed in a similar way. So notice how here you have like the maximum, right? And notice how here you have the minimum, okay? And the maximum minimum keeps on repeating. It's always the same maximum and minimum, right? So what does that help me do or identify? Well, the amplitude, right, is gonna be half the distance. What do I mean by this? From here to here, okay, from the max to the min, half of this is the amplitude. Okay, so from the max to the min, half of this is the amplitude. From the max to the min, half of this is the amplitude. I know it's starting to sound insane, but that is the main idea. The amplitude. From the max to the min, half of it is the amplitude. Okay, so what is my max in this context? Well, it's 18. What is my minimum? 4, right? So from the max to the min, half of it is the amplitude. So 18 minus 4 gives me 14. Divided by 2 gives you 7. This is a general math rule that you can do. It works in cosine always. If you're not convinced yet, let me give you another example. Imagine you have a cosine line, okay? And we know that this is a height of 2, okay? So this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4. So this is a height of 2 and this is a height of 4, okay? Well, the amplitude is going to be from here to here or from here to here, see? And so you can see very easily that, well, from 2 to 3, is 1, from 3 to 4 is also 1. And so the amplitude is 1, right? Visually appealing, makes sense on the number line. I feel like you'd be convinced. See? Now, what's the mathematical nerdy formula that you can do? The max, as I said, from the max to the min, so 4 minus 2, half of it divided by 2 is the amplitude. So 4 minus 2, oh fuck, 4 minus 2 is 2, divided by 2 gives you 1, which is the same one that I just showed you here. Alright guys, that was just to convince you that what I did here is legal, okay? And if you still don't trust me, look at the answer key. That is quite literally how they do it. 8 minus 4 divided by 2, okay? So that is how you find amplitude. In this case, from the max to the min, half of it is the amplitude. For part A, we will be putting that A equals 7. Let me take this over here. All right. So that is for part A. For part B, we need to find the value of D. So because we took a moment to really write down all the information in our diagram beforehand, it helps a lot along the way. And so you have all these tools in front of you. You have to solve this problem. You now know that A equals 7. So what is the key information I wrote down earlier? These two equations. And I know that A equals 7. So if A equals 7, well, the value of D is extremely easy. You can plug it in over here. You end up with 18 equals 7 plus D. So minus 7 minus 7, D equals 11. Just like that. So for part B, D equals 11. All right, guys, so notice that for parts A and B especially, which are 4 pretty easy points, all you really had to do was understand the sine function, okay? So I know some of you might be thinking, or you guys never really reviewed well the sine function or the cosine function or whatever, but just knowing a little bit about it already gets you 4 points, dude. I mean, all you really needed to do is understand the amplitude and the max to the min thing, and maybe understanding this example I gave of the 2 and the 4 for the maximum, for the minimum maximum, right? And that way you never forget what amplitude is, you never forget how to get it, it makes sense, and just like that, you have parts A and part B pretty easily, see? Well, you also have to plug in a point, but that isn't so crazy either. I mean, when in doubt, plug in a point. Honestly, when in doubt, just plug in a point. It's usually the way to go. So I'm just saying, guys, 4 easy points, just understanding a little bit what a cosine function is. Now it gets a little bit more juicy, right? Because here, the buzzword that shows up is find the period of the function in minutes. So that's something we haven't talked about yet. The period of a function, think about it this way. So the period of a function is from max to max or from minimum to minimum. What do I mean by this? In the case of from max to max, yeah, it would be from this guy to this guy. So whatever that distance is literally going to be the period. From the minimum to minimum, so min to min, right? It would be like from this guy to this guy, right? And this would also be, ladies and gentlemen, the period. Period. See? So the blue distance and the green distance are the same, okay? The period of the cosine function is always the same. Don't trust me? Well, it's about time that you did. If you look at this equation over here, right, which is the most generic way possible, see? This maximum is 0, 1, and this maximum is, well, 2 pi, 1. So from 2 pi, 1 to the next one is 4 pi. So the distance between these two, I know pi is in between, it's kind of scary, but dude, the distance from one max to the other is 2 pi. So you're willing to bet that the next one is going to be 6 pi. And so you're doing plus 2 pi every time. See? So that is what the period does. If I look at the minimum, you're going to end up the same thing. So if this is 3 pi, the next minimum has to be 5 pi. because the period is 2 pi. So 3 pi plus 2 pi, a whole lot of blueberry pies, 5 pies. Okay? Whatever, guys. That's just so you guys understand what the period is. Okay? So in this case, we need to figure out what the period is with the information that we have. Now, this part you have to be a little bit more creative because technically in this diagram, I would have to draw all the way over here and then find the period from here to here. See? But I don't have that. I don't have that. And I also can't graph this yet in my graphing calculator because I don't have it, you know? So how can I figure out the period? Well, what do you have? You have a high tide and a low tide. But that's not the period. Or is it? Is it the period in another way? Well, let's think about it. So if we come back to this exercise here, and I know it has the pies and it's a little bit confusing. But still, stick with me. So this maximum is 2 pi. The next one is 4 pi. And the minimum in between is 3 pi. Oh shit. Okay. What am I trying to tell you? So in this sort of diagram that we just saw, we had we had, for example, here we had 2 pi. Here, let me make another diagram or else it's gonna be hella confusing for some of us out there. So what am I trying to express? Just so that we're all on the same page. See? This thing that I have in decimals, okay, from one period to the other, right? So this is 2 pi. And when I say pi, it's like in distance. See? So this is 2 pi, right? This is 2 pi. And then and this is height of 1, okay? And this is 4 pi. And so the period, much how I said from max to max in blue, right? So the period, the period is going to be that distance. How much is that distance? Well, you do 4 pi minus 2 pi gives you 2 pi. So the period is 2, right? And imagine we don't know that this number up here is 4. Okay, we don't know that. All right, we don't know that, but we do know that the minimum right next to it is 3 pi. Ah, so what you can do is that technically from a maximum to a minimum, it is halfway of the period. Okay, so from max, distance of max to min is half a period. Okay, the distance of max to min is half a period. This distance here is how much? It's 1 pi, right? So if this is 3 pi, the distance right here is just 1 pi. And so if you add another 1 pi, you reach the 4 pi here, which is this maximum there. See? So all I'm really trying to prove or tell you is that the distance of max to min that are next to each other, right, is half a period. What do I have here? Da, 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 da. I have a max and a min that are next to each other. And so technically, if I take those two, find the distance, and multiply by 2, because here we have half, you get the full period. So right now we have half a period. I can find the full period. And so half a period, oh, look at that. We already did it. We already put the points. So half a period is from 0 to 375. Okay. And so from 0 to 375 is half a period. I'm literally going to write this first. So half a period is 375 minutes. Therefore, a full period is 375 times how much? Times 2, which gives me 750 minutes. If you want to be really, really technical about it, you would first put time between max and min is 375 minutes, right? That way you make sure you get full credit. You want to make sure you say extra stuff and exercises that have 3 points, Okay, usually when they have two or more, you have what's called method points, which is like proving that you know what you're doing, basically showing your procedure, showing your work. Whenever there's two or more points, definitely when there's three, there's procedure points. Okay, so this line right here can net you a whole ass point. I promise. See, this right here can get you a whole point. So that is 1 point. This is probably like the second point at times two, and then getting the right answer is the third point. See? All right. That is for part C. Then for part D, we need to find the value of B. All right. From here, actually, we could have done this just with part A and B. See? I'm going to show you why. But when in doubt, look at what you've done. Look at the tools you have. See? And so the tools I have, well, you have A, you have D. And so this A, I already have it. This D, I already have it. This A, I already have it. This D, I already have it. Ah, remember originally I said the problem with this second equation is that you had how many variables? It's that you had three. You plug in A, you plug in D. How many variables do you have? You have just one. You have B, which is what you're looking for actually. So 4 equals A, which is 7, times cosine 375 times B, which is what you want, plus 11. All right, and from here, okay, from here, we can try to solve it with some simple sort of algebra and stuff. See? And so because we want to get B alone, first get rid of everything that's around it, particularly on the outside. See? So on the outside, we have this plus 11. That's a little bit annoying, so I can do minus 11. So if I do minus 11, this goes away with this. I end up with negative 7, right? Yeah, I end up with negative 7 equals 7 times cosine 375 times b. What can I keep doing from here? Well, the cosine is being multiplied by 7, so you can divide by 7. So compound, you end up with negative 1 equals cosine 375 times b. Now, this next part is a little bit weird, yes, but let's understand what we have to do. So right now, the b is inside a cosine, right? Let's imagine you have 2x equals 4, and I tell you solve for x. Well, of course, you're going to tell me, duh, you divide by 2. But guys, why do you divide by 2? You divide by 2 because 2 is the inverse operation of multiply. Okay, so what is the inverse operation of cosine? Ah, the inverse operation of cosine is quite literally, ladies and gentlemen, cosine inverse. So you can do cosine inverse to both sides. And what that helps you do, well, if I go ahead and do cosine inverse over here, right? So I can do cosine inverse of negative 1. I end up with 180. So on this left side, I end up with 180 equals, well, the cosine inverse makes this go away with this. The parentheses inside, whoops, the parentheses inside stays the same. Okay, so I end up with 180 equals 375 times b. So you want to keep getting b alone, well, you divide by 375. Divide by 375 to both sides. This goes away with this. B equals 180 divided by 375. In other words, B equals, let's figure it out, 180 divided by 375. Bada bim, bada boom, 0.48. So the value of B is 0.48. That is for part D. Now guys, remember, a lot of this has been sort of fast or quicker because we plugged in the 2 points at the beginning. See? Plugging in the 2 points at the beginning, you know you're going to use these eventually. I just couldn't use them yet. Alright, but that is good procedure because you have all your alternatives right in front of you. Guys, a good procedure isn't like knowing exactly what to do and perfectly in the quickest way. Dude, screw that, okay? That doesn't matter. A good procedure is knowing all your opportunities, knowing all your options, knowing all the paths, okay? And seeing what works best. And so I first wrote down those two equations. I actually couldn't even use them immediately, but they were there, and I knew that they were there. And so the moment I found A, right? The moment I found A, I could find D. The moment I had A and D, I can find B. And the only way I can really see that if I write these equations, I use a little bit of color coding, and I remember, yeah, okay, the one on the bottom has 3 equations, the one on top has 2, and so that can help you like really approach the problem in a better way. Okay, so that is that for part D. Then they tell us that Naomi is sailing to the harbor on the morning of the 20th of January, and boats can enter or leave the harbor only when, important words, only when the depth of the water is at least 6 meters. So for part E, we need to find the latest time before 12, another keyword, before 12 to the nearest minute, sure, that Naomi can enter the harbor. Okay, let's understand this a little bit better. So they can enter or leave only when the depth of the water is at least 6 meters, or else their boat probably gets stuck or some shit like that. See? So 6 meters is just around here. See? So if I go ahead and draw a line that cuts like this, actually let me use a different color. If I draw a line that cuts like this, again, not the straightest line in the world, but you guys get the idea. We need to find the time before 12, as it says here, the latest time before 12 that Naomi can enter the harbor. And so where is 12 in my graph? So 12 is how many hours after 6? Remember that our diagram is always thinking about after 6. When t equals 0, you are at 6. When t equals 0, you are at 6. And so to reach from 6 o'clock to 12 o'clock, how many hours is it? Easy peasy, it's 6. So from 6 to 12 is 6 hours. How much is that in minutes? Well, 6 times 60 gives me 360. And so where in my graph I have 360 is exactly when it's 12 o'clock. Okay. So that means that, well, this is a 375, ¿cierto? This is a 375 from earlier. But right now, what I'm really focused on is that this here is when it's 12 o'clock. Okay? And so Naomi can enter or leave whenever we're above the famous 6 meters. And so Naomi can enter or leave anywhere around here. Naomi can enter or leave. See? Well, as a matter of fact, also over there. See? Let me be very specific. She can enter or leave here or here. Okay? And so, well, now it's pretty obvious what we have to do. We got to find this piece of time. And from that or beforehand, Naomi can enter or leave. See? Okay. So find the latest time before 12 to the nearest minute that Naomi can enter the harbor. Here, what really, really works out well, see, is understanding the following idea. This purple line equaling, like this 6, see, the moment it equals my cosine function, right, they are intersecting. Guys, when two lines intersect, they equal each other at that point. What do I mean by this? Whatever this point is, whatever this x comma y is, they both share that x comma y. So they are equal to each other. Okay, so if I create an equation for both of these lines and equal them to each other, I can find the intersect. Yeah. So my first line, we can call it 6. Y equals 6, right? Quite literally. Y equals 6 looks like that, which is what I just drew. Y equals 6. See? Let me get rid of these things. Yeah. y equals 6 is right there. See? Yeah. And the other line, well, that I have all the information now, because I finally know what A is, what B is, what D is going to be, well, is going to be blah, blah, blah. This equation, right? I just gotta plug in from all the different parts. So this equation is A, which we said was 7. So 7 cosine B we found was 0.48 times T, which is my variable, plus D, which we said was 11. So here I have my two equations and I can equal them to each other. See? Let's look at it on decimals first, just so we understand exactly what we're doing. So my first equation is up there. My second equation is 7 cosine 0.48 T plus 11. Plus 11. See? And so wherever these intersects occur, right, is basically going to be like what I need. See? So Naomi can enter or leave anywhere in this area here. See? Anywhere above that 6. Right? And technically over here as well, she can enter or leave anywhere above that 6. Now, of course, you're not going to have decimals the day of the test, but you're going to have something a little bit better. Ta-da! Your graphing calculator. See? So, y1 we can make it 6. Y2 we can make it our equation, which is 7 cosine 0.48, my variable t. In this case, I press the variable button. I get x plus 11. So if you go ahead and graph, well, there's my 6. And I clearly did something wrong. So let's check our work. y1 equals 6. y2 is 7 times cosine 0.48x plus 11. Okay, it looks right. So what is happening here? Maybe we just gotta play around with our window. See? So for the window, let's imitate what the problem gives us. So we can have a y min of 0 and a y max of 20. Okay? So y min 0, max of 20. And my x values can go from 0 to 480. See? So let's go ahead and do that. And maybe my graph makes a little more sense. Okay, awesome, awesome. I'm very glad that happened. Just to show you guys that sometimes the calculator is never wrong, okay? If anything, you're wrong. But it's good to keep that in mind because what I put in y equals wasn't wrong. I double checked it was right. So the mistake was elsewhere. The mistake was in my window. Okay, I was taking a window like too small of my graph and the lines looked both flat, which didn't make sense. I knew it. So I changed the window and now it makes sense. See? Happens to anyone. Just keep it in mind, you guys. See? All right, so back to the problem. Technically, Naomi can go enter or leave anywhere above this line. So you need to find this exact point and go and say, okay, from here backwards is when she can enter or leave. See? To find that exact point, we find the intersect because when two lines intersect, they equal each other. And so let's try to find that x, y. Let's see what it is. We can use the calc intersect trick. So we press second, right? Trace to hit the calc button. Go all the way to intersect. You can press the first curve, which usually picks it up by itself, so the flat one. And the second curve is the one that is curvy. See? Then we have guess. Guys, the guess function is really just to pick your intersect. So notice how there's an intersect here, and technically there's also an intersect all the way over there. See? And so the guess function helps you pick which intersect. It's not that your calculator is dumb and needs help finding the intersect. Nah, dude. This guess thing is for you to pick which intersect you want to know about. So I'm going to know about this one more to the left because 12 o'clock is like right there. ¿Cierto? More than that is past 12. Yeah. So that point there is 282 46811. So this point here is 282. Give me 1 second. We have 282 468 minutes, right? minutes. So from there, like backwards, is the time that Naomi can enter the harbor. See? Now, 282.468 minutes is how much after 6? Yeah. So I can take this 282, okay, 0.468 minutes, and see how many hours and minutes specifically I have here. So the first thing I can do is take that number, the 282.468, right, and divide it by 60. So what this gives me is that I end up with, well, I end up with 4.7, right, 4.7078 hours, right? Another way that you can kind of try to approach it, see, which now that I think about it is a little bit more intuitive. So if you divided it by 60, you got 4 point something hours, see? So 4 hours enter nicely into this. And then this amount here is like some amount of minutes, right? All right, so I got 4 point something, so that means I can put 4 hours here, see? Now how much is 4 hours? Well, 4 hours is 4 times 60, which is 240. So I can write that this number here is the same as 240 minutes, okay, plus the remainder. So I can do 282. I can do this 282 minus the 240. So the remainder is 42.468 minutes. If you want to get really technical, you can say that this is 4 hours plus the 42 minutes. See? Now, because it's to the nearest minute and because the context of the question, it makes sense to round down. That's fine. Well, and you are rounding down because this is 4. You can leave it as 4 hours and 42 minutes. Now, from 6 o'clock plus the 4 hours and 42 minutes, how much time is it? Well, 4 hours, 7, 8, 9, 10, plus the 42 minutes, 10, 42. Notice how this is worth 4 points, so you definitely want to be writing a lot of these different method points and stuff, see? But that is for part E. So the latest time before 12 is 10:42. All right, it makes sense to round down because we're thinking about like the nearest minute beforehand, right? So that is for part E. Got it? Then for part F, it says find the length of time in minutes between 6 and 3 on the 20th of January, during which Naomi cannot enter or leave the harbor. So the first question, of course, is where exactly can she cannot where can she cannot enter or leave the harbor? So we just found that 10:42 and like before that she can enter or leave. So right here, this right here is the famous 10:42. That thing in blue is 12 o'clock, and whatever this is going to be my length of time. See? So actually, where's 3 o'clock? See, because they are telling us between 6 and 3 o'clock. And so 3 o'clock from 6 to 3 o'clock is how many hours? It's going to be 6. It's going to be, well, from 6, right, to 15. Oh, here it's more easy. You can do 15 minus 6. 9 hours. See? 9 hours, well, 9 times 60, 540 minutes. And so the 540 is around here. See? So basically, the exercise is asking you, okay, in this function, between 6, which is what I'm seeing here, and 3 o'clock, which is here. Wait, was it from 6 to 3? Yeah, from 6 to 3. So from all of this part, where is it that Naomi cannot enter or leave? So the only place she cannot enter or leave is when it's below 6 meters, and the only part of my diagram that is below 6 meters is this sliver right here. And so if I find the intersect on the left, which I just did from part E actually, which is 10:42 minutes, I mean at 10:42, if I just find whatever time is here, well, that is going to be my length of time. See? And so, once again, watch how the B likes to do it. Part F needed something from part E. It's not always the case, but today it was. See? And so, I can open up my graphic calculator, I can go to my y equals, and remember how I said that using the intersect, you can pick which intersect with guess. So, pick your first curve, pick your second curve, and with guess, pick your second intersect. And so if I pick this second intersect just around here, right, it's the same as picking or asking my calculator what this point is. See? Which is exactly what we want. Go ahead and guess. There it is. And so that right here is 467 minutes. So 467, let me write it down, 0.53, okay, 0.53, 1 minutes. Okay? And so technically, if we want to be really clear about it, well, I can divide this number by 6, follow a little bit the process of before, just so that we're on the same page. So this divided by 60, sorry, gives me 7 point something. So that means I can put 7 hours into this with ease. So 7 times 60, yeah, 420. So this is 420 minutes plus the remainder. So 467.531 minus 420, an excellent number, gives you 47.531 minutes, right? Now the 420 minutes is the same as 7 hours. See, so I can write this as 7 hours plus 47 minutes. See? And so from 6 to 7 hours plus 47 minutes, well, you do plus 7, so 6 plus 7 gives you 13. So you end up with 13 hours, 47 minutes. See? So this right here is 13 hours, so 1 o'clock with 47 minutes. Okay? And so if I do 1 o'clock, 47 minutes, minus 10 o'clock, 42 minutes, well, how much do you end up with? You end up with 3 hours and 5 minutes. See? And I know that subtracting time like this can be a little bit weird, but if you take your time, I'm sure you're gonna get it. So this minus 1042, I think it was, yes, minus this. You can think about it this way. On the one hand, you have the hours being subtracted to each other, okay? And on the other hand, right? On the other hand, you have the minutes being subtracted to each other. So this gives me 3 hours. This gives me 5 minutes, which is the same as saying that this is 180 minutes plus 5 minutes gives you 185 minutes. See? All right, that was a little bit more extensive and a longer way to get like the answer. But just so you know, I wanted to show like how you manage time, how you deal with time in a mathematical perspective. A quicker way to solve this, I'm just showing you the long way so you understand what's going on behind the scenes, okay? Like this is what we're doing at the end of the day. We're taking 2 times and subtracting them, see? A quicker way to do this, now that you saw the boring way, a quicker way to do this is that you just take the equivalent in minutes. So this one is this one. Meanwhile, this one, oops, I actually fucked that up, sorry. Let me go with that again. I'm leaving that in the video because we can all fuck up. So this one, the 467 minutes, is this one. Well, that's farther out. And this one, the 282 minutes, is this one. The one that's earlier. See? And so technically, here I did green minus red, right? Well, let's do that again. Let's do green minus red up here. So we can take that 467.531 minutes minus what's in red, which is 282.468. lo and behold, you still get 185 minutes. See? So, a quicker way to do it, but I think it's a little less intuitive if I'm telling you to subtract these minutes. I'd rather first show you what's really going on, right? You're subtracting 1 o'clock with 47 minutes to 10 o'clock with 42 minutes, but you can put it all in minutes and it's the same way. See? So green minus red is the way to go. That is part F. And as I said, you guys, this exercise is not that hard, but it is awfully specific. Okay, if you're not familiar with the period and the amplitude and all that shit, there's not much you can do. I'll be honest. There's not much you can do. But just knowing a little bit about it, just understanding what amplitude is, memorizing or learning this thing, right? What the period is, or learning this thing, that from a max to a min is half a period, or learning this thing that from the max to the min, half of it is the amplitude, or visually what the amplitude is. Just that, which is not too crazy, you guys, but just that is enough to net you quite a few points. So, there goes the exercise, the problem number 3. I hope it helped. Alright guys, for this fourth one, we have the famous tree diagram. And so they tell us that a large international sports team tests their athletes for banned substances. Okay? They interpret a positive test result as meaning that the athlete uses banned substances. So it's positive if they use. A negative test result means that they do not. The probability that an athlete uses banned substances is estimated to be 0.06. And so, especially for probability problems, you need to really check if everything that they give you is in your diagram or not. Okay? Do not take it for granted. Double check. Usually in geometry and trigonometry, whatever they say like here is gonna be in the diagram. Okay, usually. Almost always, in my experience, is practically almost like always, okay? But for probability and stuff like that, they don't always put it. See? For example, this first one, the probability that an athlete uses banned substances is estimated to be 0.06. And so uses bad substances, kapow, 0.06, there it is. See? And so this first one, it's what they tell me is already in the diagram. Okay, we're happy with that, ¿cierto? Cool. This next one we have if an athlete uses bad substances, so kapow, the probability that they will test positive is 0.71. So that is kapow, 0.71, there it is. It is also in my diagram, see? Notice how in this case we had like a two-stepper, ¿cierto? Como kapow, kapow. And this is because if an athlete uses banned substances, so I'm in this part of the world, the probability will test positive, I go this way, see? So whenever they put the if word, very important, sort of like a conditional probability, stuff like that, you are going a certain direction, you are limiting part of your options. See? Why does it limit part of my options? Because when they say if they use banned substances, you know you're in the banned substance world. You actually forget about everything else up top and you only look at the bottom. Okay, that is the power of the if. That is the power of the conditional probability. Anyways, whatever. This second thing, the 0.71, does show up in my diagram, so I am relaxed. Okay? And this last part, as we can see, has if an athlete does not use banned substances, so kapow, now I'm going this way, does not use, right? The probability that they will test negative is 0.98. And so this testing negative right here, the 0.98, I have to put it, and I got to put it right there. 0.98. See? Let me make that a little more pretty. So 0.98. All right, I don't know how much prettier that was or not, but whatever. Point is, this third thing, I now just put it into my diagram. There it is, there's 0.98. So now I'm ready to do part A, which says using the information given, copy, blah, 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 complete the tree diagram. See? Now, these are some really easy 2 points. and you just have to know the intuition of the tree diagram. So I'm going to take a little bit of time explaining it. And the rest is going to be a little faster, see? Anyways, in the world of probabilities, ladies and gentlemen, your probability basically has to add up to 1. Okay, and I know that right now sounds a little bit weird, but your probability has to add up to 1. All right, there's a couple of things going on here. See, on the one hand, when you consider all scenarios, the probability of everything added up together has to equal to 1. See? On the other hand, because it adds up to 1, this 1 tells me that it's, where is my equal sign? This 1 means 100%. So 0.5 means that it's 50%, and 0.05 is 0.0, sorry, it's 5%. If you memorize these three numbers, you're good to go to find anything. For example, I can tell you, well, what is this in percent? And you look at these other cases, you get the intuition, you know that you have to move the 0 a couple times. This is going to be 0.7%. Kapow. Just like that. And I can also give you 0.13%, and you'll tell me, see, that is 0.0013. Whatever, man. You can go from decimals to percents. That's what I'm trying to say. And 1 is 100%, and your probability has to add up to 1. Why? Let's say you're leaving school, for the day. You got tired of the AB. You just want to go home and play, I don't know, League of Legends and fall into depression or something because it's League of Legends. And so if we talk about what you do when you go home, right? The things you can do once you leave school, right? You might tell me there's a 50% chance I go home. You might tell me there's a 32% chance I go, I don't know, for a walk. Maybe there's an 8% chance that you go get something to eat. See? And then there's a 10% of maybe just whatever, sleeping. Okay? Point is, you can put a lot of percents here. You can put all the different scenarios that you want. But these percents add up to how much, ladies and gentlemen? These percents, lo and behold, add up to, and this is the dramatic moment, all of these percents add up to 100. That is the point of probability. That is what I mean, that your probability has to add up to 1. If you consider all the different scenarios, your probability has to add up to 100%. Okay? The thing is, in a tree diagram, you don't have all these different options. I mean, if I were to try to express this in a tree diagram, it would literally look like this. Okay, that would be my first part of my tree. This might be my second. Okay, it's confusing, it's hard. See? And so the cool thing about the tree diagram is that it simplifies it a lot. It says, okay, so instead of taking all these crazy scenarios and different scenarios, you have to boil it down to 2. And so there's either, I don't know, a 50% chance that you go home or a 50% chance that you play League of Legends. Okay? And these numbers can be different. Maybe it's 35, and over here it would be, I don't know, 565, right? These numbers can change, but it's only 2 options. Okay, so the tree diagram boils it down to 2 options. Okay, that's the main idea. It boils it down to 2 options, and your probability has to add up to 1. Okay, why is this useful? Why is this guy on YouTube saying all this shit? He's saying all this shit because in a tree diagram, there's only 2 options, and because your probability adds up to 1, then that tells you the massive piece of information that this plus this is 100%. That this plus this is 100%. And that this plus this is 100%. Okay. Okay, so for example here, when they use bad sums as this, and they test positive, and you get 71%, well, this plus this is 100, and so 0. So my 100, right, my 1 minus 0.71 is the testing negative? Oh shit. So this is 0.29. Okay. Okay. Tell me more. Tell me more. And so if you keep filling in the tree diagram like that, keeping in mind the two options, the thing that they add up to 100%, what do you discover? That over here, when they use banned substances and you get 6%, the probability that they don't use banned substances is 0.94. Because 1 minus 0.06 is 94. Guys, that is the key idea, okay? Tree diagrams, they add up to 100%, each of the two like sticks, see? Each of the two alternatives. And the reason this happens, which is actually in your formula booklet, is this thing called complementary events, okay? What this means is that you either go to them all or you don't, okay? You either flip a coin and get heads or you get tails. There's only two scenarios, you know? And so those two scenarios added up together add up to 100, see? What is this PA and this PA with an asterisk? PA is the probability of A, and PA with an asterisk is like, with apostrophe, sorry, is the probability of not A. Okay, whenever they put like a little symbol thing, it's like not this. See? So the probability of A plus not A has to equal 100% because it is all the scenarios. You either go to them all or you do not go to them all, and the probability of those added up together is 100% because it's the only scenarios that you have. It's only two options, ¿cierto? Okay, so when they do not use banned substances and they test negative, it's 98%. So that means that when they test positive, it has to be 2%. All right, guys, I know that explanation was a little bit long, but now you are a master at tree diagrams, and that's what really matters. Okay? So that is for part A. Later on, they tell us that we need to determine, and this is now a little bit quicker, but let me just show you the intuition. Yeah? Here we have that we need to determine the probability that a randomly selected athlete does not use banned substances and tests negative. All right, guys, there's a lot going on here. See? And I'm sure from class you've seen that sometimes you multiply probabilities and other times you add probabilities. See? And so some of you are probably wondering, when the heck do you use one? When the heck do you use another? You've probably asked your teacher. He's probably giving you some different tips and tricks. The best one that I can give you is that when we multiply probabilities, we need to think of the word and. When we add probabilities, we need to think of the word or. So and is that it happens at the same time, and or is that like it can happen, okay? But it's not necessarily at the same time. Uno o el otro, este es el y. Uno o el otro, y este es el y. All right, whatever. A little bit of Spanish, doesn't matter. um, and so, guys, where's the athlete that does not use banned substances? So that means for this in green, ¿cierto? Does not use banned substances, so we're going this way. And, so we're going to be multiplying, tests negative. So it's 0.94 and 0.98. What almost everyone does is that for part BI, they just write 0.98 because, oh, it's like what they reach, ¿cierto? No. Because there's an and in between, you have to multiply, okay? It's like you enter this world and you end up here. What's the probability of that, okay? That means you gotta do 0.98 times, sorry, 0.94, because of this 4, 0.94 times 0.98, see? Which is this here. Why did that happen? Because whenever you see the word and, you're gonna be multiplying, okay? Cool. So you go ahead and do that. For part BI, the answer is 0.921. So, oops, claro. It would be 0.94 times 0.98. This gives you 0.9212, if I'm not mistaken. If you use three significant figures, it's 0.921 because you count 1, 2, 3. Do you round it up or down? You keep it the same, 0.921. As a percent, it's 92.1%. All right, that is part BI. See, part B double I. Okay, part B double I. I'm running out of space, but that's fine. Part B double I is if two athletes are selected at random, calculate the probability that both athletes, okay, so it's two athletes, okay, important, do not use banned substances and both test negative. So it's the same as part BI, like up top, but it happens twice. Ah, okay. So if I were to think about this in words, really think about and or, we have that for part B double I, and this is why it's very important to use the and or words. We have that the first athlete does not use banned substances and test negative, and second athlete does not use banned substances and tests negative. All right, let me put this somewhere where we can see it. Yeah. So as you can see, if you look at my and words that I'm putting in between, we have an and here, we have an and here, we have an and here. And let's also recall that this first part is what we got from part BI. What was the probability? 0.921. 2, ¿cierto? Okay, so that means I'm going to have this 0.912. I'm going to have 0.9212 right here. I have this and, which lets me multiply, and I have another 0.9212. And so 0.9212 times 0.9212 gives me whatever that is. See? So the answer for part B double I is going to be 0.848609. You can leave it as three significant figures with 0.849 or just, 84.9%. All right, so I know that right now some of you might be a little bit confused, but the biggest idea I have to share is that when you multiply, when you see the word and in the world of probabilities, you multiply. See? And so think about it this way. In order to reach this 98, how do you reach the 98? First you go this way, then you go that way. So first it is a does not use banned substances and tests negative. That is like the biggest idea you can get out of this, okay? Anyways, that is for part B. For part C, we need to calculate the probability that a randomly selected athlete will receive an incorrect test result. Now notice, incorrect is in bold. What are the incorrect test results scenarios? All right, so let's put in red, or actually, let's put in purple the scenarios that are incorrect. An incorrect test result. Not a negative, an incorrect. For example, if someone does not use banned substances but gets a positive test result, then it's fake news. It's literally fake news. They don't use substances, they got tested positive. Here we have something that is incorrect. And so one of the scenarios that I just put in purple is that they do not use and they test positive. Okay, they do not use and they test positive. Okay, so that is the incorrect test result. So that is one scenario. Whoops. So we have that they do not use banned substances. That gives us 0.94. And this is the multiply. They test positive 0.02. Or, kapound, there's a plus sign. Or they use banned substances. Right, uses. But they test negative. And so they didn't get caught, basically. They didn't get caught. So that would be 0.06 and 0 points times, ¿cierto? And 0.29. See? Again, I know this is confusing, so let me go over it just one more time real quick. We have that they do not use, for the first scenario of incorrect, they do not use and test positive. So do not use and test positive, or use and test negative. Okay, that is explanation of each of the numbers, why it's multiply, why it's add. See? So once you have all of that written out, once it makes sense, the adding and multiplying and all that shit, you can put that 0.94 times 0.02 plus 0.06 times 0.29. And see what happens. You get this. This is the answer for part CI. Okay? So that's going to be 0.0362, which is the same as if I tell you 3.62%. Then for part CII, we have that a random sample of 1,300 athletes at the tournament are selected for testing. Calculate the expected number of athletes in the sample that will receive an incorrect test result. Now, probability is not hard in terms of math, like you're just adding and multiplying shit, but it's very hard to understand why you're doing what you're doing, okay? And so an expected number, el número esperado de algo, ¿cierto? So the expected number is sort of like, I don't know, I think it's easier to explain with a different example. So let's say that just some random shit, ¿cierto? Let's say that we have a dice, okay? Like a dice, a die, six-sided die, ¿cierto? So you have, I don't know, uh, 1, 2, 3, 4, 5, 6 here, 1, 2, 3, 4, 5. This kind of die, see? Un dado, one. Yeah, it's a dice, see? So this dice has 6 sides, right? It has a side with a 1, with a 2, with a 3, with a 4, with a 5, with a 6. It's a 6-sided die, and what is the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6? Well, it's 6 sides, ¿cierto? So for getting a 1, it is 1 out of 6. For getting a 2, it is one of the sides. It is 1 out of 6. So it's 1 over 6 for each number, ¿cierto? If you roll the die, it's 1 out of 6 of getting any of the sides, ¿cierto? Unless it's a loaded die, unless it's like an illegal die, and whatever, see? So probability is 1 over 6 for each side, see? Para cada cara. And so let's say, whatever, man. Like, there's 1,000 people. There's 1,000 of us, see? And we all take one die and throw it at the same time. What is the expected number of fours that we're going to have? How many fours do you think we're going to have if 1,000 people throw this dice at the same time? Well, you're going to take that 1,000, multiply it by the probability of getting a 4, which is this 1 over 6, ¿cierto? And that is the expected number of fours we're going to have when 1,000 people roll the dice. How much is this? Around 166. Let's leave it at 167, see? So around 167 people will get a 4 when they roll a dice. Now that is the expected value, okay, the theoretical value. What actually happens, you're going to see it in real life, and let me tell you, it can be very different, see? But what's expected, what's most common, is that we would get 167 people rolling a dice. I mean, rolling a 4, okay? So again, what's the context? There's 1,000 people, they all roll a dice. What is the what is the expected value of 4s that we're gonna get? Well, the probability of rolling a 4 is 1 over 6, so you take that 1,000 and multiply it by 1 over 6. Ah, so you take your amount of people, n, and multiply it by its probability. Okay. And so in my formal booklet, when you look up expected value, you have this weird thing right here, ¿cierto? Notice how I said it was n times p, so the amount of people times the probability of that thing happening. Well, over here, in a very, very, very fancy way, this right here is P, and this right here, the sum of all your x's is n. Oh, okay, okay. It just makes a lot more sense if I say n times p, right? And if I say the 1,000 people and all that shit. The formula booklet, though, gets way more fancy. And they have to get more fancy. I can't blame them. See, this is like the way you should write it, okay? But whatever, man. We're human beings. We like the intuition, the intuitive version, and so n times p. That's what I'm trying to tell you. For expected number, you're gonna be thinking n times p. What is my n? We have 1,300 athletes. What is the probability that they will receive an incorrect test result? Well, that comes from part CI, so it's gonna be 1,300 times 0.0362, which is the you know the probability of getting an incorrect test result, and that is going to give me 1,300 times 0.0362 gives me just around 47.06 people. See? 47.06 people, basically. So yeah, if you want to, three significant figures, count 1, 2, 3, this guy, do you round it up or down? You round it up, so it's 47.1. See? That is for part C, part double I. Now, there's something here I can show you that does not have to do with probability, but will help you for whenever you do the test. Notice how this is worth like a million fucking points. It's worth 5 points. See? So what that means, okay, usually when it's worth more than 1 point, usually, okay, definitely when it's worth more than 2, is that you have what they call method points, okay? Method points, de metodología, see? So what that means is that you can have the wrong answer, but the right process and get points. Okay, this is just something I want to show you quick, because it's important that you guys know. Over here, as you can see, for question 4, the one we're looking at, you have endpoints here, cierto? Endpoints here. What this means is that you can get method points for, right here, cierto? Right here, they're doing n times p. And basically, you get a method point if your n is correct, because they gave you 1,300, but your p is wrong. If your n is correct, but your p is wrong, you still get 1 method point, okay? And as you can see, for what's coming, there's a lot of method points all over the fucking place. See, there's method points here, there, etc. What I'm trying to say is, get points where you can. It doesn't matter that it's not 100% correct. You can still get method points. Okay, that's all I'm trying to say, guys. The other thing is that because there's method points, what you needed for part C double I came from part C I. And that's a very common thing, that for part C you need something from part B. Okay, the IB loves to do that, okay? Especially for any section that has part I, part double I, those are definitely connected, dude. So just keep it in mind, you guys. All right, these are test hints, tips and tricks. Everything adds up. Everything helps. Okay? All right, let's move on. Here we have that Team X. That's an interesting name. Team X are competing in a tournament. There are 20 athletes in this team, and it is known that none of the athletes in Team X use banned substances. And so none of these guys use banned substances. And we need to calculate the probability that none of the athletes in Team X will test positive. All right. This right here is weird. I'm just going to say right away, it's a little bit weird. Okay? What is the main idea? Right now, we're seeing if they test positive or not. Okay? And for testing positive or not, see, we have, give me 1 second. Yeah. For testing positive or not, knowing that none of them, cierto? Notice how here it says none. So none of the athletes in Team X are use banned substances. That means I am in the world that is, let me make a little bit of space because I know I wrote a lot of shit earlier. So if none of them use banned substances, that means I am in the world that is up here. So suddenly, for this part of the exercise, I do not give a fuck about anything down there. This is what I'm working with right now. What's up top? Okay, cool. So we need to calculate the probability that none of the athletes in Team X will test positive. When you work with a binomial distribution, okay, it's when you have only two options, which is what I have right now. I mean, right now, with what they told me, I am in this world here. There is nothing else. This is the only thing in my world. See, they either test positive or negative, period. And so binomial distributions is when you have two scenarios. See, usually it's like, oh, you toss a coin, head or tails. But for these tests of positive or negative, it's either positive or it's negative. And so it's also two scenarios. See? And so one way to do this is that you take the 0.98, multiply it literally like 20 times. ¿Cierto? And that would work. See? That would literally work. You can solve it doing that. So you can do 0.98 to the power of 20. There is your answer. See? Now, there's another way to do this that I would like to show you because it's important to get familiar with the calculator. See? And so when you have your graphing calculator and you identify it's a binomial world because it's only two scenarios and I'm only in this part of my tree diagram, ¿cierto? So it's literally only two scenarios. You can go to the distribution menu, which is pressing second bars, see, to hit that distribution button, and go all the way down to where we have binomial, see? So as you can see, there's a bunch of shit over here. You have binomial, Poisson, geometric. These are different distributions, you guys. Okay, you even have the normal one up here, the most common one, ¿cierto? In this case, you have binomial PDF and CDF, see? Now, they both actually ask for the same shit. So PDF asks for trials, the probability for P, and then an X value, see? Paste is just enter. The binomial CDF, right, asks for the same crap. So what's the difference? Well, I'm immediately going to say, guys, some of your calculators, the CDF is a little different, see? But the classic, the TI-84, we have that the binomial PDF is the probability of that amount of that exact amount, see? And binomial CDF is the probability of that amount or less. As I was saying, right, we're in the world of either testing positive or testing negative. We have the amount of trials is 20 because there are 20 athletes, and we're looking for the probability that none of them will test positive. And so my X value is 0 because we're talking about none, ¿cierto? Now, what is my probability? Well, I am in the world of testing positive, and so for testing positive, my my probability for P is going to be 0.02. So this is going to be my P. And so if I go ahead and put into my calculator, normal PDF, because it's going exactly for 0, I have 20 over there. My P is going to be 0.02, and my exact value is going to be 0. See? All right. Go ahead and paste. There it is, which is the same that I got earlier, going like this. See? And so there you have the two ways in order to do it or solve it. See? I urge you to get used to the binomial PDF CDF manner because for some exercises you just have to do it that way. Okay? You can try to do it by hand, but it's fucking annoying. See? Although I think it's kind of cool that you guys maybe know now what your calculator does behind the scenes. Okay? For this next part, the same idea goes down. We need to determine the probability that more than two athletes in Team X will test positive. More than two. See? Now let's remember that I said that binomial CDF gives me that amount or less. And so what I can do actually is that because we're not talking about an exact value anymore, before it was exactly none, ¿cierto? Now it's 2 or more. I can go to my distribution. I can put the amount of trials, which is 20, because I still have 20 athletes, ¿cierto? That hasn't changed. The probability for testing positive, we said, was 0.02. Okay, cool. And it's more than 2, right? So if I put 2 here, what this gives me, actually, because it's the world of CDF, it's the probability of that amount of less. So what I just found is that probability that less than 2 athletes in Team X will test positive is around 0.992931. See? And so right now, what the exercise is asking for is more than, right? And I just found less than because the calculator CDF works in less than. See? That amount or less. I'm going to say right away, some modern calculators, okay? You can like skip the next step I'm going to do because you ask for it to face the other way to look for more than immediately. See? The thing is, in the TI-84, it's always going to give you less than. See? And so right now I just got the less than version, ¿cierto? Now what's the opposite of less than? It's more than. And so guys, this all comes back to the tree diagram, which is the cool part about this exercise, ¿cierto? It's either one thing or another. Your probability has to add up to 1. So it's either more than or less than. You either go to them all or you don't. You either test positive or you don't. And so if less than is 0.992931, then the version of more than is 1 minus 0.992931. And this actually comes from here because from the complementary events world, right? You have that, I don't know, let's say this is my less than version, ¿cierto? Less than, and this is more than, see? In order to find more than, you can do the more than is the PA with the apostrophe equals 1 minus P of less than. See what I mean? Which is what I just did here. Ah, okay. So you put that into a calculator, 1 minus this, bada bim bada boom, kapow. You get 0.00706. 0.00706. And so 0.768. So if you go ahead and do 3 significant figures, you count 1, 2, 3, you do round it up or down, you round it up, so that it gives you 0.00707, which is the same as, well, you can just leave it like that, honestly. The answer key leaves it like that, and that is how you solve it. See? So ladies and gentlemen, number 4 was a hard tree diagram problem, but you also now know pretty much everything you need to know about tree diagrams. So I hope it helped. I'll see you around, and number 5 is coming up. Alright, so for number 5, the last one, we have that a large closed container in the shape of a half cylinder with a rectangular lid, so this whole thing is a half cylinder and it has a rectangular lid on the top, is to be constructed with a volume of 0.8 meters cubed. And so the volume inside all of it is 0.8 meters cubed. Okay. It has a length of L meters, which is this guy here, and the radius of R meters, which is this guy here. See? So radius, radius, radius. See? Okay, so all of those are R, whatever, there's my radius. See? Alright, cool. For part A, we need to find an exact expression, okay, for L in terms of R and pi. Alright, interesting. So what is L? L is the length of meters. See? And I know some of you right now might be thinking, damn, what the heck do I do? Well, what is the context of the problem? What are the keywords? Let's read it again. A large closed container in the shape of half cylinder with a rectangular lid is to be constructed, blah, 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 volume of 0.8 meters cubed. Has a length of L, radius of R. So we have shapes, and they give us the volume. Okay. Your formula booklet doesn't have something that it can help. Why, yes, of course. The formula booklet, you guys, oh, by the way, important to get used to it. The day of the test, you got no sleep, but you do have your formula booklet, and you do have the graphic calculator. Get familiar with the formula booklet. It's a tool that you can use. Go down, geometry and trigonometry, page 6 and 7, 6 and 7. Ah, so here I have a bunch of volumes, see? What was I dealing with again? We were dealing with half a cylinder. Volume of a sphere, volume of a sphere, cone, right pyramid, cone. Okay, so there I do not have the volume of a cylinder, unfortunately. So let's look again, maybe up here. Ah, for some reason, it's for numbers and algebra. I don't know why, but this is all, I mean, in prior learning. This is why it's important to get familiar with the formal booklet to know what's in it. I know that the volume of a cylinder is in here, I just wasn't sure where. So I keep digging, I keep trying to find bada bim bada boom. Volume of a cylinder, there it is. So volume of a cylinder, let me just write it down. Volume of a cylinder is pi r squared times h. Now this is the volume of a full cylinder. So the volume of a half cylinder is the same thing, just that divided by 2. So the volume that we will be working with is pi r squared h, all of it divided by 2. So this is the volume of half a cylinder that we're going to be working with today. Now what do I know about uh, this equation? So they tell us that r is the radius and h is the height. Alright, but quirozmath, here we're working with L. Okay, but this container, which is half a cylinder, which is on the floor, yes, this is length, but if you stand it up, it's going to look something like this. Yo, my art skills today. Look at that. God damn. So if you draw the cylinder, okay, it's going to look something like that, right? There's your cylinder, and this L, which is this part here, what does it look like? Ah, it's the height. So because of the context, important to understand the context of the question, this h is really just going to be L. See? And what is our mission? Well, we need to find an exact expression for L in terms of r and pi. Now, what is that trying to tell me more intuitively? Is that you want to reach L equals r something something, pi something something. Okay? Why does it help to look at it this way? Because all you really need to do now is get L alone from here. Get L alone. That is the compass. See? That is your north. Try to get L alone. Why get L alone? Because they tell you. Find L in terms of this and this. So find L equals something, this and this. Okay, cool. So from here, well, first things first, volume is 0.8. So I can start off by saying 0.8 equals pi r squared, L divided by 2. Get L alone. First things first, I would multiply by 2. So multiply by 2 to both sides, bada bam, bada boom, 0.8 times 2, trust me on this, it's going to be 0.8 times 2, about 1.6. 1.6 equals pi r squared L. You still need to get L alone, right? What is bothering L? Pi is bothering L, and r squared is bothering L. So I can start by dividing by pi to both sides. So this goes away with this. I end up with 1.6 divided by pi equals r squared L. Okay, how do I get rid of this r squared? Well, what is r squared doing to L? It's multiplying. So again, divide by r squared, divide by r squared, which I know looks kind of weird, but technically it's just going to go on the bottom with this pi. So bada bing, bada boom. I end up with final answer L equals 1.6 divided by r squared times pi. Here I have L equals something something r something something pi. I don't care how it ends up. I just care that L is alone. See? Cool. So that, you guys, is quite literally part A. Not that hard, right? Just gotta go slow and understand what the formula booklet has, what it offers, etc. So this is gonna be for part A. Cool. Then they tell us that the container will be constructed using 2 different materials because they want to make this question hard. The material for both the curved surface and the rectangular lid on the container costs 4.40 per square meter. So this part here, right, which also goes all the way around, right, is going to be 4.4, and this guy up here is also going to be 4.4. See? Then it tells us the material for the semicircular ends of the container, okay, will be P per square meter. So what's in green costs P per square meter, which is also the green that is back here hidden as a semicircle, right? Okay, so that is what they're trying to say. See? So the cost C of the materials to construct the container can be written in terms of R and P, where P is greater than 0 and R is greater than 0. Okay, sure. For part B, we need to show that the cost of the container is this whole thing here. See? You guys, whenever they put the word show that, it means that this is a fact. Okay? And so it can also be a hint for how you need to build it or construct it. Okay? But basically, you need to reach this. See? So start from C, right? Try to construct yourself the cost of all these curved surfaces to find this C here. See, that is like the big challenge. Now, why am I taking a mini break here? Because when it says show that, and this is a fact, that means that for finding the derivative of C in respects to R in part C, you can use this. And so, interestingly, when it says show that, and you take it for granted as a fact, you can skip part B and do part C. Now, of course, try to get all the points possible. This is worth 4 points. Hopefully, don't skip it. But if you're low on time and you see the derivative and you're like, damn, I know I can do the derivative quick, but I can't do part B, ladies and gentlemen, you don't need to do part B. You can do part C, get those 3 points, and not have time to do part B and not get 4 points, but whatever, man. You're getting points where you can. See? So that is just a small hint. When it says show that, and whatever you need in part C, you use from part B, and this thing is show that, well, you can just do part C immediately. See? So there's a quick hint in case you're low on time and you notice something says show that and you can do the thing right next to it. Consider that. See? Just want to give you all the tools possible for whenever you face the IB. So, we gotta find a way to express the cost. See? Now, keywords. See? Blah, blah, blah. Because we're talking about the surface, okay? Because we're talking about a surface, we are talking about surface area, okay? Think about it this way. Take this shape, dip it in chocolate, and see all the ways in which the chocolate covers it. Okay, that is all the surface area you need to account for. See? So what surface area am I accounting for exactly? Well, on the one hand, and actually we're gonna need a lot more space for this. So, all right, and so from here, we can notice a couple things. Yes, it's one rectangle plus two of these, right? Plus that half sort of area thing. See? All right. And also, these have different costs associated because the IB is a little bit mean and they say they use two different materials. And so, what am I trying to say? I'm trying to say that the curved surface, so that is this guy, and the rectangular lid, which is this guy, both of them have a cost of what? 4.40 per square meter. So, because it's a cost function, I need to multiply these by 4.40. So 4.40 times, and over here I have 4.40 times. See? All right, cool. On the other hand, the semicircular end, which is this guy in the middle, right, has a cost of what? Of P per square meter. So I know it sounds a little bit weird, but over here, I'm going to put times P. All right, and so now I just need to dig into the formula booklet and try to find the area, so the surface area for each of these. See? So on the one on the left, well, I have 4.40 times the area of a rectangle. Now the area of a rectangle, right? And I'm pretty sure this is not in your formula booklet. So here you have area of a lot of stuff. Maybe parallelogram can kind of fit here. Whatever, it's base times height. See, so you have a rectangle. I don't know, this is 2, this is 3. The area is going to be 2 times 3. Okay? Yeah, in this case, the area, I mean, my dimensions are L and R twice. So here I have R, here I have R, so it's going to be 2R. See? Just to leave it very clear, this is L, and over here is 2R. So let's write that. L times 2R. On the other hand, I have, well, plus 2P times the area of half a circle. So what is the area of a circle? Formula booklet, area of a circle. There it is. Area of a circle is pi r squared. Now notice, this is the area of pi r squared. This is the area of a full circle. So what is the area of half a circle? You take this guy and you divide it by 2. That's that. And last but not least, I have the area of this sort of like cylinder part. See? So what is the area of the curved side of a cylinder? All right, that is insanely specific, but so is the formula booklet. So here we have area of the curved surface of a cylinder, and as we can see, right, it says 2 pi rh, right? And you might already be thinking, okay, but what is h? We already had that discussion. H is the height of a cylinder that looks something like this. See? So this is the area of a cylinder. I mean, sorry, the height of a cylinder is this. See? But in this exercise, this was tilted sideways, right? And so h was kept here, and they cut it in half. They cut it in half. You end up with something like that, ¿cierto? It got cut in half, right? But h is still h. See? H is still h, h is still h, h is still h. And in this context, they called HL. See? Just because it's tipped sideways, but technically it's still the height of the cylinder if it were standing up. So this h is really just going to be L. That means if I follow the formula, we're going to have 2 pi RL. Now, important point, much how over here we had half a circle, here, this is the area of the full curved surface of a cylinder. Our cylinder, as they tell us in the exercise, keyword, we are dealing with half a cylinder. So this formula, we gotta divide it by 2. Quite literally, over here, gotta divide by 2 because it's half a cylinder, not the full cylinder. So now, ladies and gentlemen, I am ready to go ahead. All right, so cost equals, on this left side, I have, well, this 4.40 can interact with this 2, so I end up with 8.80 L times R, see? Then over here, this guy can go away with this guy because of fractions. I end up with pi r squared P. And here on the right side, well, this guy can go away with this guy. Simplifies my life a little bit. I end up with 4.40 pi RL. And right now, we're pretty happy. This looks pretty comfortable. I go ahead, I look at what we need to show. Does it say? It says something a little different. See? It says something a little different. So you're probably going to come here, look at this and say, damn, dude, I suck at math, dude. I'm so far away, man. Fuck. But really, take a moment, take a breather, and look at it more closely. What is the main difference between this here in part B and this that I have here? What is it? Ah, there is no L here. And here there is an L. There's an L here. There's an L here. What is the way in which I can express L? Ah, in part A, we found the exact expression for L. Look at that, how convenient. So L equals, let me write it up here, L equals 1.6 divided by r squared times pi. And so once again, ladies and gentlemen, as you've probably seen in my videos, sometimes, but not always, sometimes part B uses something from part A. And that can be a massive hint going forward. It's not always the case, but take a second and think about it, because if you think about it, it might certainly become very obvious what you have to do. See? So go ahead, plug in L. We have that C equals 8.80 times L, which is, yeah, sure. So this L is multiplying everything, see? Notice how 2 times 3 times 4 gives you, damn, I'm slow today, gives you 24, see? Which is the same as 4 times 3 times 2. I mean, you might have been thinking, okay, this gives me 6, this is 4, 6 times 4, 24. Here, you're thinking 4 times 3 is 12, 12 times 2 also gives you 24. What am I trying to say? When things are multiplying, the order doesn't matter. You're still going to end up with 24. Okay, so just to make this easier on myself, I'm first going to write 8.80 times r, and on the last part, I'm going to put times L. And L was, as we said, 1.6 divided by r squared pi. All right, plus pi r squared p, that doesn't change, plus 4.40 pi r, L is at the end, I feel comfortable with that, 1.6 divided by r squared pi. All right, so now I can play around and understand a little bit better what's going on. So, because here we are multiplying fractions, fractions just multiply straight ahead. So technically here you can do 8.8 times 1.6 times r. And at the bottom you're going to have 1 times 1 times r squared times pi. Now no one writes 1 times 1 because that doesn't really change anything. Any number times 1 stays the same. All right, cool. So on the left side it looks like that. See? Yeah. The one on the middle, does it change? It does not. Stays the same. There's nothing I can do. Pi r squared times p. And here on the right side, a similar idea, I end up with 4.40 times 1.6 times pi times r. And over here, I have r squared times pi. All right, so now we're nearing the end of this exercise. So on the one hand, I can do this famous 8.8 times 1.6, right? So that gives me 14.08 times r divided by r squared times pi. Here in the middle, pi r squared times p does not change. And here on the right side, I end up with 4.4 times 1.6. So a little bit different, 7.04 times pi times r divided by r squared times pi. Yeah, and now we gotta do a little bit of a math trick, see? So, just so you guys understand really what I'm about to do, if I take this guy here, and I show it to you more closely over there, so here I have 14.08 times r divided by, that is an r, divided by r squared. Now what does r squared do? What does r squared do? So if you have 2 and you have it squared, it's the same as writing 4. Okay, yes, but what happens in between? You have 2 times 2. 2 cubed is 8, but what happens in between? You have 2 times 2 times 2. Ah, so if you have x squared, it's the same as x times x. All right, cool. So down here I have r squared, which is the same as r times r. And here goes the pi. Why does this help? Because now I understand that this goes away with this. You end up with c equals 14.08. I have 1 r left on the bottom times pi. Ah, okay. So here on the right side, I can do something similar. I can understand that this goes away with this. And the same thing happens. This one gets rested by 1. This one disappears. And so you end up with 7.04 divided by r just once. All right, and so now I'm feeling a little bit more comfortable. Now I have something very, very similar to what I need to reach. I go over here and I see how it's similar. So that, notice that it starts with the one that has just R. So the one that is just R is this guy here. So let me write C equals, let me write C equals 7.04 divided by R. Then it goes with the one that has a pi on the bottom. See? And this other thing's kind of weird, but we'll get there. See, it has the one that has pi on the bottom. So pi on the bottom is this guy, right? So I'm going to go ahead and put plus 14.08 divided by r pi. And last but not least, I have the triple p pi r. My p is at the last part, but again, 2 times 3 times 4 is the same as 4 times 3 times 2. So I can rewrite it as I please because it's all being multiplied. So I'm going to leave it as the exercise asks. P then pi then r. P then pi then r. See? And here, technically, you're good to go, but I'm sure some of you are thinking like, yo, what the hell, dude? I don't think I know what this is. What the fuck is that? It looks weird, I know, but I got you. Relax, don't worry. See? What the negative exponent does, ladies and gentlemen, is always the same thing. The negative exponent, what it does is flip it. So, negative exponent flips your flips your thing, because it can be a variable, it can be a number, flips your thing. See? Example. 2 to the power of negative 1 is going to be 1 over 2. 2 to the power of negative 2 is going to be 1 over 4. Or actually, the step in between is that it's going to be 2 to the power of 2 equals 1 over 4. So notice how this negative exponent, first, you put the whole thing on the bottom, and then you sort of like do the exponent and end up with 4 on the bottom. See? That is what the negative exponent does. And so if you have x to the power negative 1, you end up with 1 over x. If you have x to the power negative 2, you end up with 1 over x squared. I know some of you might be thinking, okay, but why? Why does that happen? I never understood. Math is so confusing. Math is oftentimes also called the study of patterns. The big question is, did we create math or discover it? There are so many patterns in this world. Did we find a way to express it, or was it already there? I don't know. But that is a question for another day. For now, let's focus on the study of patterns. See? Example, 2 to the power of 3, 2 squared, 2 to the power of 1. See? So this is just a mini lesson on how negative exponents work. And you're also going to discover why anything to the power of 0 is equal to 1. See? So mini lesson, you can skip ahead if you want, whatever. 2 to the power of 3, we said is 2 times 2 times 2, which is going to be 8. 2 squared is 2 times 2, which gives you 4. 2 to the power of 1 is just 2, which gives you 2. And 2 to the power of 0 is 1 because you've been taught that anything to the power of 0 is equal to 1. Let's understand why. The reason this happens, you guys, is because, notice, to go from 2 to the power of 1 to 2 squared, what do you do? From 2 to 4, you do times 2. From 4 to 8, you do times 2. But what if you gotta go backwards? What if you gotta go from 8 to 4? 8 to 4, divide by 2. 4 to 2, divide by 2. 2 to 1, divide by 2. So 2 divided by 2 gives you 1. And so in any pattern that you discover, eventually you're going to have the same number being divided by itself, which is why it gives you 1. 3 squared, 9. 3 to the power 1 is 3. From 9 to 3, you divide by 3. Here you divide by 3 again. So it's 3 divided by 3. It's itself being divided by itself. The same as here, itself divided by itself. Itself divided by itself, you end up with 1. So that is why anything to the power of 0 is equal to 1 because you're dividing it by itself. See? But what if you take it a step further and you say, fuck society, let's keep going. If you keep going, 1 divided by 2 is how much? 1/2. But if you divide by 2 again, ah, so it's 2 to the power negative 2, you end up with 1 divided by 2 divided by 2 again, so it's going to be times 1/2, which is the same as 1 over 2 squared, which is the same as 1 over 4. Okay, so that is why the negative exponent sort of flips it, because you're dividing, see? Keep in mind that if you have 1 divided by 2 to the power negative 2, you still flip it. So this would go on top first, so you end up with 2 squared equals 4. What do I mean by this? If you have 1 divided by, I don't know, x to the power negative 4, you put it on top. If you start off on top, you put it on the bottom. Okay? Different examples, same idea, negative exponents, you flip it. See? This thing about multiplying and dividing, another way you can think about it is that in each of these scenarios, technically you're always multiplying by 1. See? And so if in this case you divide by 2, you're getting rid of one of them. So there you only have 2. If you divide by 2 again, you're getting rid of another one. And if you divide by 2 again, you're getting rid of this one. What do you end up with? With just 1. That is another way you can think about it. Technically, everything is always being multiplied by 1. See? Alright, whatever. Whatever floats your boat. Just a mini sort of thing to understand exponents. And so over here, if I force you, because again, I'm forcing you because over here it says show that. See? So you got to reach the same thing. If here it has an r to the power negative 1, we'll put this r on top. Put this r on top. What do you need to do? You want to flip it, right? You want to put it on top. And so you flip it, you put a negative exponent. Kapow. Over here, what are they asking for? They're asking for you to flip just r. Pi doesn't matter, you flip just r. So if you flip just r, well, it's on the bottom, right? You want to put it up top, do the negative exponent, you're flipping it, there it is. Okay, and last but not least, this thing doesn't change. And there is the show that they're looking for. Okay, that was a little bit long, but there was a lot to do and a lot to clear up. See, the biggest thing I would like to show you, or really be clear about, I think the best way to find the cost is do something like this. Okay, draw a couple diagrams, color it in, take your time, and be very wary of how the functions change. Okay, I mean how the formulas change. The IB loves to do this. They love to give you half squares. And so you got to consider that it's 2 squares, but the formula changes, you divide by 2. A classic is, for example, this cylinder, right? It's easy to forget that it's half of the whole curved cylinder, so you got to divide by 2. In fact, the first time I did this video, I did not notice, okay? It can happen to anyone. And then I realized, and I was like, damn, I forgot to divide by 2. See? It can happen to anyone. Take a moment, draw it, consider it, and know that the IB tries to catch you with that. That way you don't fall for it yourself. See? So this part B was a little bit long, but I'm sure it was worth it. So there it is, part B. Part C, you need to find DC over DR. I'm sure some of you are already thinking, damn, what the heck is this? I don't know. DC over DR is, lo and behold, the derivative. See? When you do the derivative, it helps you maximize, find the optimum, find the slope. See? What do I mean by this? Originally, when you have any function, okay? When you have any function, for example, f of x equals, I don't know, f of x equals, actually, so f of x equals 3x plus 2, see? Technically, right now, if you do like an xy table on this, right, you're going to end up with a bunch of set of points. So if x is 1, y is 5. If x is 2, y is going to be 8. See? And so this gives you sets of points. This gives you 1,5. This gives you 2,8. See? The moment you do the derivative, okay, what happens is that now you don't get set of points. But what you will get is that this whole thing is now slope. And this is sort of like, if you plug in, I don't know, x equals 2, now you'd be asking, what is the slope when x equals 2? Instead, before, you were asking, what is the slope? What is the y value when x equals 2? All right, so very different things. The moment you do the derivative, it helps you find slope. And if you plug in anything for x, you're asking the function, what is the slope with this value of x? In this other hand, you're finding the value of y when you plug in an x. See? All right, beautiful. So now we understand a little bit better what derivative does, and further down the line, you're going to understand why it's even useful in the first place. So, finding the derivative of this, well, it's a little bit easier than what you think. And as I said, because it's show that, you can jump to this right away. Why am I saying this? Derivative exercises are usually pretty fast. I gotta be honest, they're usually pretty fast given the amount of points they give. You can probably do this in like a minute and a half and it gives you 3 points. That is a pretty good investment. So I'm just saying, derivative problems, do that shit right away, get those easy points. I'm just saying. I've always noticed that derivative problems give you way too many points for the amount of time it takes. So we're trying to do the derivative. See, so I'm going to put here derivative. There you have it. Derivative of x to the power of n. Really, what it says here, in other words, is derivative of an exponent. Guys, I have a video on the derivative of an exponent. You can check it out. But very, very intuitively, what we're going to see, and you can see it here as well, ¿cierto? Is that the exponent is going to drop in front and you will subtract it by 1. That is all that happens. That is literally all that happens. So if you have x squared and you do the derivative, the 2 goes down in front, so it's going to be 2x, and you do minus 1 to the derivative. So you end up with x to the power of 1, which is the same as just leaving it as 2x. Let's do another example, just so that we're very clear on this. If I have, I don't know, 3x squared. Not 3x cubed, 3x cubed, see? Whoops, 3x cubed. If you do the derivative of this, you end up with 3 times 3 times x to the power of 3 minus 1. So that means I end up with 9x squared. The derivative of 3x cubed is 9x squared. That is the derivative of an exponent. Pretty simple, right? Over here, it looks a little bit more nasty because we have some variables going around here or there, and it's just kind of weird, see? But something cool is that when they did the show that and they asked you to put the r on top, it helps you to do the derivative. What am I trying to say here? Sometimes putting all your variables on top, even with a negative exponent, helps you do the derivative. In fact, that's why they did it this way, to make your life easier. Whoa, AB is trying to make my life easier? Ladies and gentlemen, sometimes they do, to your surprise. And so because you have this r on top, now it's easier to do the derivative of an exponent. If it were on the bottom, and I'm like, do the derivative of this, that's hella hard. But if I ask you, do the derivative of this, that's a little bit more easy, isn't it? ¿Cierto? It's more intuitive how the exponent plays. So now, for finding this derivative, I can do, let me put small thickness. Okay, so this guy is going to multiply in front, so I'm going to have 7.04 times negative 1, r minus 1 minus 1. So that is the term on the left, see? For the term on the right, it's awfully similar. You're going to have 14.08 times negative 1. All of this still divided by pi times r. ¿Cierto? This is all the times. Negative 1 to a minus 1. Plus, well, this 2 is going to multiply this whole thing. So you're going to end up with 2 pi r, 2 pi r, 2 minus 1. Okay, so this first term ends up being negative, so negative 7.04 r to the power negative 2 minus, because there's a minus here, 14.08 divided by pi times r to the power negative 2 plus the only one that says positive 2p pi r to the power of 1, because it's to the power of 1, you just don't really write it. So that is part C. Really fast for the amount of points it takes. Super intuitive. Consider doing that right away. Not gonna lie. All right, so that is for part C. Let me just double check that it is okay. Taking a good look, looks just fine to me. All right, cool. So now for part D, they ask us, or they tell us that. Let me just highlight this for a second. Yeah, there it is. They tell us that the cost of materials to construct the container is minimized. Big word. Big word. Minimized when the radius of the container R is 0.7, and to find the value of P. So here, the keyword is minimized. And now we need to understand a little bit better what derivatives are good for. And so I did tell you just a minute ago that when you do the derivative, you are now talking about slope. Okay, why is slope useful for optimization? So here's a little bit of 101 on why slope is useful for optimization. Sorry, why derivatives is useful for optimization. Hint has to do with slope. So let's say you have something that looks, sure. Let's say you have something that looks like that. Okay? And let's say, I don't know, over here it's production. I know here it's earnings. See? And so maybe you're thinking about how many brownies, you gotta cook for a bake sale and sell them at school. If you make too many brownies, you're not gonna sell them all. You're gonna lose money because some brownies are not gonna get sold. And if you make too little, well, you're not gonna sell enough. People are gonna be hungry, and you weren't able to sell enough for the people. So those are the two extremes, right? Over here is a situation where you make too many brownies, you gotta throw some of them out, you lose money. See? Over here is the case where you did too little and you could have sold more. And over here is the perfect amount where, you know, everyone was happy with the amount of brownies, mm, everyone was fed, and whatever, not one brownie was thrown into the trash can. See? Yeah. How do you reach that point? Well, this point here, ladies and gentlemen, is in a quadratic, the vertex. See? Guys, a vertex is always one of two things. It's either a maximum or a minimum. In this case, we have, yes, we have a maximum, ¿cierto? Because it's up here. A minimum would be something that looks like that. See? The lowest point, a maximum is highest point. Dale? All right, cool. So, to reach a vertex in a quadratic, there's a couple ways. See? Today I'm going to show you the way through derivatives. And so, there's a key idea we need to understand. When you do the derivative, so you end up with f of this, ¿cierto? This whole thing is slope. See? This whole thing is slope. And so what you can do, right, is understand the following. At this first part, for example, at x equals 1, see, over here, what is the slope? Well, if you draw a line here to signify, oops, let me try that again. If you draw a line here to signify the slope, it looks something like that, see? There it is. This is what we call a tangent, okay? A tangent is something that touches once and never again at a certain point. So the tangent at x equals 1 is a straight line that helps me see the slope. And so if you plug in like this, that's going to give you the slope at x equals 1. It's going to give you the slope of that line. See? Now, if we eyeball it, it's positive, right? And it's growing, so this would probably be, I don't know, it's going to be like 2. See? If I make another line down, and if I find another slope over here, see, and I draw a line here, well, what's the slope of this one, you guys? Well, it's still growing, so it's still positive, but it's a little less, isn't it? So instead of 2, I'm going to put 1, see? And if you keep going and you keep drawing lines until you reach the vertex, Ah. All right, here comes like the big O moment, see? So over here, right at the vertex, you have a slope of what? Ladies and gentlemen, you have a slope of, it's a horizontal line. Look at this. Look at my amazing art skills. 0 degrees. Boom. It's a horizontal line, isn't it? So m equals 0. Why is it 0? Because gradient, which is the same as slope, which is the same as m, they tell us is y2 minus y1 divided by x2 minus x1. Oops, minus, there we go, minus x1. So, is it changing in my x values, this blue line? This blue line, is it changing in x values? Why, yes, of course it's changing in x values. Is it changing in y values? It's staying at the same one. So, it's staying at the same one, so up here it's going to be 0, and on the bottom it's going to be x2 minus x1. So it's 0 divided by something. 0 divided by something is always going to be 0. So my slope at the maximum, okay, holy shit, someone write that down. My slope at the maximum is equal to 0. And I can do the same thing. My slope at the minimum is equal to 0. So, ladies and gentlemen, if you want to optimize something, find where its slope is equal to 0. Bada bim, bada boom. Couple of hearts, because I'm just saying this is a big, big, big thing you just realized. If you want to optimize something, find where its slope is equal to 0. Damn. So the first thing you gotta do over here is that you take dc divided by dr and you equal it to 0. Guys, I shit you not, just by doing that, you get 1 point. You literally get 1 point. And it's a method point, which is knowing the procedure, knowing what to do. So this already gave you 1 point. It's just the idea that I just shared, filled with a bunch of hearts, that gave you 1 point. So take your slope, equal it to 0. Take your derivative, equal it to 0. Same idea. You want the slope of 0 because it's going to help you find the vertex, helps you find the max or min. Even in a graph like this, you do the same process. So this is going to be, I don't know, a -2. This is going to be like a -1. And here, boom, it's going to be a 0. And later on, sure, whatever, it ends up being 0.5. Then it ends up being like, I don't know, 3. See? But m is 0 at the optimum, okay? So, you equal this to 0, and you try to find the value of b. So, if this whole thing equals 0, that means I can say 0 equals -7.04, and they tell me as well that r is 0.7 by context of the problem. So I'm going to put 0.7 to the power of -2 minus 14.08 divided by pi times, what is r? R is 0.7 to the power of -2 plus 2p pi r. They tell me that r is 0.7. And so from here, you can solve the problem a little more easily. See? So we're going to be plugging in a lot of numbers. This is going to take a little bit, but at least now we understand very well what is going on and why it's going on. See? Which is the most important thing you can do. Really understand the intuition of the problem. So let me take a screenshot and let's do some hardcore math because that's what we're here to do. So we're going to need a shit ton of space because this exercise is fucked up, but that's fine. So we need to get p alone. See, and I just plugged in a bunch of numbers. Let's see what happens. So this 0 stays as 0, whatever, ¿cierto? This first term, let's find out. We have negative, actually I can do this whole thing immediately. See? So this whole thing is going to be negative 7.04 times 0.7 squared right? Squared negatively, sorry, minus, going to put a fraction using alpha y equals to hit F1, 14.08 divided by pi times 0.7 to the power of -2, okay, plus, actually I just leave it there, so I'm not going to do the last part because I can't, right? But this right here is going to give me negative 23.51. I'm just going to put the whole number, I don't care, 388,408, see? And now I find this last part over here, see what P is. So P is being affected by 2 times pi times 0.7. So I'm going to do exactly that. 2 times pi times 0.7. So I have 4.39,822,9715 P. So you want to get P alone, right? Well, P is being affected by a multiplication and also something being added slash subtracted. So here I can do plus 23,513,88,408 to both sides. Golden rule of algebra, always do it to both sides. So here I end up with 23.51388,408 equals 4.398229,715 P. You can do significant figures, but for some reason I didn't. I don't care, whatever. Here I can divide because it's being multiplied. 915. So this goes away with this. Here I divide the 23 by this long ass number. And so P equals this. See, so P equals this 23, well, positive, ¿cierto? So let me just write a positive 23.51388,408 divided by this other number. P is going to equal 5.34 621 5547. Let me just mega double check over here. Oops, that's the formula booklet, wrong one. Let me just mega double check, but it should be right. Yes, it's correct. If you want to put significant figures now, you can count 1, 2, 3. Round it up or down. You round it up because it's a 6. You can leave it as 5.35. Remember your units. Dollars per what thing? Square meter. All right, so that, you guys, is finding the value of P, or part D. Not super hard, but you do need to understand what you're doing, see? The moment you equal the derivative to 0, everything just kind of flows, and I hope now you understand better why. Why did we do it? Because it is the key thing for optimization. If you want to optimize something, as it says here, find where its slope is equal to 0, okay? That is why we start off with this very important step right there. So finding the slope equal to 0. Yeah. Then they tell us that in total, 350 containers will be constructed at this minimum cost, and to calculate the cost of materials to the nearest dollar to construct all 350 containers. So they give us the value of P, right? And each container, how do I find the cost of one container, you guys? So this derivative helps me find the value of P, okay? Which is this thing here, right? But what is the cost of one container? I gotta go all the way back. Gotta go back to my original function for C. Okay, so my cost function, which is what I did all the way over here, is right there, right? And I just found my value of P. So my cost function now changed a little bit just for plugging in P. So P, as we said, just give me a second. P, as we said, was 5.35. So 5.35 pi r squared. So now my cost function changed to this, right? All right, and they also tell you that the container is minimized, right, from this part. The container is minimized when R is 0.7. So I can also plug in 0.7 for R. So all of these can have a 0.7 plugged in. See? 0.7, 0.7, 0.7. And so this, ladies and gentlemen, is the cost of what? It's the cost of one container. See? And I know this looks nasty, but these are all just numbers. I just gotta add, subtract, etc. See what happens. Pi is just a very long number. Let's not forget that pi is, you don't have to memorize it, a very long number. See? So, this looks nasty, but it's just numbers. Take it easy. Put it into your calculator, see what happens. So I'm going to have 7.04 times 0.7 to the power of negative 1. Just the 0.7 to the power of negative 1. Careful with that. Then I'm going to be adding a fraction, which goes 14.08 times 0.7, and only the 0.7 is to the power of negative 1. Oops, negative 1. Yeah. And then down here, I'm going to have pi. Easy as that. And last but not least, I'm going to have this 5.35 times the pi times the famous 0.7, this time squared. So what does that give me? This gives me the cost of a single container. The cost of a single container is 24.6895 from my calculator. See? All right, so this is cost of one container. One container. What is the cost that they're asking for? Exactly, they're asking for 350 containers. So you take this one container, you multiply by 350, and you end up with your 350 containers. So take this number, multiply by 350, and there are the cost of your 350 containers, which is exactly 86 8643.39. See? 1397. Now, you're not quite done yet because there is an important disclaimer at the end of this exercise. They tell you that you need to answer to the nearest dollar. So what is the nearest dollar in this case? What is the nearest dollar in this case? So here you just need to round like consciously, right? And so I know some of you might be thinking, oh, here, well, I got to round down because of this 39, right? And so you're going to leave it as 8643. And although you're right from a math perspective, you would be slightly wrong from a context perspective. Because if you're trying to produce these containers, right? And you show up to your manufacturer with $8,643, he's going to say, yo, where are my 39 cents? And so, because of this context, you got to round it to 8,644 because you got to be able to pay the guy. And I know 39 cents, it's like, dude, is he really going to whoop my ass for 39 cents? Some people do. So pay him the extra dollar. Given the context, you got to round it up. See? $8,644. And just so you know, if you got something a little different, right? If maybe you didn't do these long numbers over here, right? If you did significant figures over here, you can get a slightly different answer, and the IB takes this into account. Just so you guys are a little bit more relaxed, look at the answer key here. It says accept answers between 8641 and 8645 due to routing the value. See? So keep that in mind. It considers, like these small decimal changes and this or that, but because of context, round it up. Okay? Those 39 cents, they matter, and you're answering to the nearest dollar, you gotta put it $1 up. See? All right, that is for part E. And now we're almost done. Don't worry. Part F, they tell us that the materials for constructing the containers can be purchased at a discount according to the information in the table. Yeah. So If the cost of your materials is between $1,000 and $2,500, you have a 1% discount. And as you keep adding more cost to your materials, you get a bigger discount. Why does this make sense? Well, it's actually an incentive. If you put something like this, you're gonna try to have your consumers or whatever ask for more containers, and so your client is gonna ask for more for more work from you, and you're happy with that, cierto? You want your client to be happy. You want him to have an incentive to spend more on you. And so, yes, you're making a discount. Yes, you might be losing some money. But think about it this way: if you didn't do any discount, maybe your client would buy this. See, he would send containers in this amount. But with the discount, your client is more prone to saying, "Okay, with this discount, I think I would do it over here," and you're both happier because of the discount. See? So that is why discounts exist in the first place, and it also makes sense, right? I mean, the more you buy, like producing in bulk tends to be cheaper. See? Okay, I got a little bit economist there, but it's true. Economies of scale, all of that crap. Yup. Anyways, here we have part F. Determine the cost of materials for 350 containers after the discount is applied. So the cost of materials, as I found out, is 8644. So that means I'm in the range of 8%. And so I gotta do an 8% discount to this amount, the 8644. And so there's two ways to do this, you guys. I'm gonna show you the way I like to do it. So technically, if I do the discount, right, the original price, which is 100%, right, 100%, I'm gonna subtract it. Instead of paying 100% of the price, I'm now paying 100% minus 8% of it. See? So what does this mean? I end up with 8644 parentheses 92%. Now, how do you express 92 as a percent? You leave it as 0.92. Why? Well, 1 is 100%, 0.5 is 50%, 0.05 is 5%, which means that 0.005 is 0.5%. As long as you memorize just some of these, you're going to be able to convert decimals to percent and the other way around effectively. What is happening behind the scenes? You're just divided by 100. See, so 50 divided by 100 gives you 0.5. 5 divided by 100 gives you 0.05. If you don't trust me, well, it's about time you did. 5 divided by 100, 0.05. See? 50 divided by 100, 0.5. So that is how you get those whatever from percent to decimal. Okay. Why do you do it to decimal? Because then you can plug it in to your calculator. So this in my calculator is going to be 8644 0.92. There it is. And so the cost of materials, right? The cost of materials is now going to drop to 7952.48. See? Give me a moment. All right, sounds about right. See? And so here you get 2 points, one side for method, another one for your answer. See? Now, as we saw before, the answer from part E can oscillate a little, it can change a little, right? Depending on whether you use decimals or not. And so here the method is super important. It's very important that you show this. Okay, find your way to show it, but do it. I'm going to show one more way because I know some people like it to do it a little different, cierto? So what you can do is that you can first find the amount of discount that you get. So for example, if I do 8644 and I multiply it by 0.08, which is 8%, cierto? What is this number? This number is the amount of discount I am getting. It's not the total cost of materials, it's the amount of discount. So I will get discounted $691.52 with this discount. And so you can take your original amount, 8644, subtract it, 691.52, and end up with, lo and behold, 7,952.48. Don't trust me? It's about time you did. This minus this gives you the same number. See? So those are two different ways to do it. You can either find like how much you're going to get discounted and then subtract it from your OG amount, or from the OG amount, find how much is going to be like sort of like the total left. So from 100%, you subtract 8%, 92%, put it in decimal, bada bing, bada boom. Guys, whatever is more intuitive for you, stick to it. You're the mathematician here, not me. You're the one that faces the test, not me. Find what works for you, find what's reliable. And the biggest message in all of my videos, you guys, is find the right procedure. Okay, there are method points all over these tests. And if you understand the method, if you understand the procedure, you will for sure get at least a 4. And with a couple marks here or there, you're gonna get a 5. Okay, it's that simple. And I know most of you just want a 4 or a 5, so stick to that. Stick to the procedure, learn the formula booklet, learn what's in your graphing calculator, and you're gonna be just fine. All right? A 6 or 7 is attainable with more studying, more exercises, but a 4 or a 5 should be certified, you guys. Okay? Graphing calculator, formula booklet, and just a little bit of faith in yourself, and you'll get there. Ladies and gentlemen, that is for number 5, and that is actually for this whole paper too. I hope it helped. I'll see you around.